Hello there, and welcome to Life Beyond Seen, where curiosity drifts gently and science takes the scenic route toward rest. Tonight's slow voyage is about something older than mountains, deeper than imagination, and more mysterious than the far side of the moon. It's about the ocean, not the postcard kind that laps at your toes during a summer holiday, but the boundless blue wilderness that wraps around our world and hides almost everything it contains. The ocean is where life began, and where most of it still lives. It shapes our climate, drives our weather, feeds billions, and holds stories we haven't even begun to read. And yet, for all our satellites, submarines, and ambitions, we've barely skimmed its surface. Most of what lies beneath remains untouched, unseen, and unknown. That's what we're here to think about tonight. Why exploring the whole ocean may be one of the most impossible quests humanity has ever dreamed of. Before we set sail into that question, I want to ask you something simple. Where in the world are you listening from right now, and how far are you from the sea? Maybe you can hear waves if you open a window, or maybe you're hundreds of miles inland where the only water nearby is a kettle about to boil. It's a comforting thought, isn't it? That no matter where we stand, the ocean is always there, quietly pulsing at the edges of our maps, waiting with its endless patience. And if you find this slow exploration soothing, or if it helps you wind down and let the day slip away, I'd be grateful if you gave this video a like, maybe even subscribed. It helps this small corner of calm reach others who might need a peaceful pause too. So let's begin gently, without rushing. Imagine for a moment that you're looking out across the sea from a quiet shore. Maybe the air smells faintly of salt. The water stretches out before you, shifting and shimmering as if the earth itself were breathing. At first glance it feels knowable. Boats trace lines across its surface. Satellites watch its tides from space. Scientists drop sensors into its depths. And yet, that vastness hides something we cannot truly grasp. More than 70% of Earth is covered by ocean, and of that, more than 80% remains unmapped, unobserved, and unexplored. We often talk about space as humanity's final frontier, but in reality we know far more about the surface of Mars than we do about the bottom of our own seas. That discrepancy isn't for lack of trying. It's because the ocean resists us. It resists our machines, our senses, and sometimes even our imaginations. Our relationship with the sea is ancient. Before we mapped continents or charted stars, we followed coastlines and currents. The ocean carried us to new lands, fed us, and terrified us in equal measure. It was the unknown just beyond the horizon, and for much of history we treated it that way. A vast, restless border between places, not a place itself. Even now, most of our lives unfold without ever thinking much about what's beneath the waves. We picture the sea as a single, continuous body of water, but it's more like an intricate world layered beneath our feet. The shallow shelves near continents teem with familiar life, but plunge beyond them and the world changes completely. Light disappears. Pressure rises to crushing extremes. Temperatures plummet. Landscapes twist into alien forms, and within that environment, countless forms of life thrive, many of them beyond anything we've yet encountered. If the ocean were a building, humans have barely explored the lobby, and yet the temptation to go deeper is irresistible. It's in our nature to want to see what's hidden, to name the unknown, to understand what lies beyond the next ridge. We've sent divers to the continental shelf, submersibles into deep trenches, and robotic explorers crawling across the seabed like mechanical crabs. We've mapped parts of the ocean floor using sonar from ships and satellites that infer depth from the way gravity tugs on water. And still, the picture we have is patchy and incomplete. Some of the most detailed maps we've made of the ocean's depths have resolutions of only a few kilometers. Imagine trying to navigate a city with a map that shows only vague outlines of its streets and none of its buildings. That's roughly our current view of Earth's largest ecosystem. The scale of the challenge becomes clearer when you consider the sheer size of what we're dealing with. Earth's oceans hold about 1.35 billion cubic kilometers of water. Their average depth is nearly 4 kilometres, and their deepest point, the Challenger Deep in the Mariana Trench, plunges nearly 11 kilometres below the surface. To put that in perspective, if you dropped Mount Everest into the Mariana Trench, its peak would still be more than 2 kilometres underwater. The ocean's vastness is not just horizontal, but vertical. Each kilometre down brings exponential increases in pressure, decreases in light, and changes in the physical and chemical properties of water. The deeper you go, the stranger the world becomes. And that world is not empty. Scientists estimate that as much as 90% of marine species remain undiscovered. Every deep-sea expedition brings back creatures no one has ever seen before. Ghostly fish with transparent heads, shrimp that shoot glowing jets of chemicals, bacteria that thrive around hydrothermal vents hotter than boiling water. The deep ocean is not a barren wasteland, but a dynamic, thriving realm shaped by forces that operate on scales of time and space we can barely comprehend. Yet it's a realm we visit rarely and briefly. The total time humans have spent at the deepest part of the ocean is measured in hours, not days. Fewer people have been to the Challenger Deep than have walked on the moon. This is the paradox of the ocean. It surrounds us, sustains us, and shapes our world. Yet it remains largely beyond our reach. And the deeper we try to go, the more impossible the task becomes. The water itself becomes our greatest obstacle. Pressure increases by 1 atmosphere, the equivalent of the weight of Earth's atmosphere at sea level for every 10 metres of depth. At the bottom of the Mariana Trench, pressures exceed 1,000 atmospheres. That's more than 8 tons per square inch. At those depths, even small flaws in a submersible's hull can be catastrophic. Electronics fail. Materials behave unpredictably. Human bodies are crushed long before they reach such depths without the protection of specially engineered vessels. Light, too, abandons us. Sunlight penetrates only about 200 metres into the ocean, and beyond 1,000 metres, there's only darkness. This means that much of the ocean is a lightless world where vision is useless, and exploration depends on sonar, radar, or the dim glow of artificial lamps. Even those tools have limits. Light scatters and absorbs quickly in water, and sound waves distort and reflect unpredictably. Navigation becomes guesswork. Mapping becomes an exercise in probability. What lies beyond the reach of our instruments might as well be invisible. Then there's the matter of distance. The ocean is not just deep, it's vast. Its total surface area is about 361 million square kilometres, and beneath that surface lies a seafloor that's more rugged than any mountain range on land. Trenches, ridges, seamounts, and abyssal plains stretch across distances that dwarf our most ambitious exploration missions. Even with modern ships and autonomous vehicles, systematically mapping every square metre of that terrain would take centuries. And that's just the seafloor. The water column above it, an immense 3-dimensional habitat, adds another layer of complexity. Life is not neatly distributed like trees on land. It drifts, swarms, and migrates in ways that are difficult to predict and nearly impossible to track completely. All of this explains why, even after centuries of exploration, the vast majority of the ocean remains unknown. But unknown doesn't mean empty. It means that the ocean holds secrets we haven't yet uncovered. Geological features that reshape our understanding of Earth's history, ecosystems that challenge our definitions of life, chemical processes that might inspire new technologies or medicines. Every dive, every sample, every expedition is a reminder of how much we don't know. And every answer we find raises new questions. This is also why exploring the ocean isn't just about curiosity. It's essential. The ocean regulates our climate, absorbing about a quarter of the carbon dioxide we produce and most of the excess heat trapped by greenhouse gases. It drives weather patterns, sustains fisheries, and supports economies. The deep sea holds resources from rare minerals to potential new antibiotics. Understanding the ocean isn't just about satisfying our wonder, it's about understanding our planet and our future. And yet, the more we learn, the clearer it becomes that we may never know it all. Some people find that idea frustrating, that a place so close to us can remain so hidden. But maybe that's part of the ocean's allure. Its inaccessibility is not a flaw to be solved, but a feature to be respected. It reminds us that not everything is ours to conquer, that some parts of the world remain beyond our reach, and perhaps always will. And in a way, that's comforting. It means there are still frontiers left, mysteries still waiting. It means that even in a world mapped by GPS and scanned by satellites, there are still places that resist definition. The ocean's vastness is humbling, but it's also grounding. It reminds us that our technologies, powerful as they are, have limits. We can launch telescopes that see galaxies billions of light years away, but we still struggle to see clearly a few kilometers beneath the waves. That tension between what we can imagine and what we can actually do is at the heart of the story we're telling tonight, and it's a story that's just beginning. Because if understanding the ocean starts with acknowledging its scale, the next step is understanding just how deceptive that scale can be. The ocean we think we know is only a fraction of the ocean that exists, and the deeper we look, the more it seems to stretch away from us, layer by layer, into something we might never fully grasp. So, as we stand here on the shore, looking out across that seemingly endless horizon, it's worth remembering that what we see is only the surface. Beneath it lies a world as complex and varied as anything we've ever encountered. A world that resists exploration not because it is unwilling to reveal itself, but because it operates on scales and terms that are profoundly different from our own. And in that difference lies the heart of the mystery we're about to explore. Because to understand why exploring the whole ocean is impossible, we have to start by examining the illusion that we already know what the ocean is. When most of us picture the ocean, what comes to mind is something familiar and comforting, the kind of image found on postcards or screensavers. Rolling waves, turquoise shallows, maybe the glimmer of sunlight dancing on the surface. It's the kind of ocean we know from holidays, from childhood trips to the shore, from the sound of waves used in sleep apps. It feels vast when you stand beside it, but also accessible, like a friend you've known all your life. Boats travel across it, surfers play in its waves, fishermen work its edges, children collect shells in its tidal pools. This surface view has shaped how we think of the ocean for as long as we've lived near it. But what feels familiar is really just the thinnest layer, the skin of something unimaginably larger. The water we swim in, sail across and photograph at sunset represents a fraction so small it's almost misleading. If you dipped your hands in the sea while standing on a beach, you would be touching what oceanographers call the epipelagic zone, the top 200 meters of water where light still penetrates. It is here that photosynthesis happens, where most of the ocean's visible life exists, and where almost all of human interaction with the sea has taken place. Dolphins leap, coral reefs thrive, and shoals of fish glint like silver rain in the sun. It is dazzling and beautiful, but it is not the ocean in its entirety. It's more like the outer foyer of a cathedral compared to the vast chambers within. When people talk about knowing the ocean, they usually mean this accessible surface zone. We've spent centuries fishing it, charting it, crisscrossing it with trade routes, and watching its storms shape our coasts. We've given names to currents and tracked their seasonal shifts. We've studied plankton blooms, measured water temperatures, and catalogued species from the shoreline to the reefs. This is the ocean we think we understand, the one that feels tangible. But that impression of familiarity masks the fact that this surface is only a sliver. Beyond those 200 meters, light fades and pressure builds, and the ocean begins to reveal itself as something far stranger than the everyday image suggests. Still, this surface layer holds enormous influence over human life. It's where our food comes from, with billions depending on fisheries for protein. It's where trade moves, with container ships carrying nearly 90% of global goods. It's where storms brew, gathering heat and moisture before unleashing hurricanes and typhoons. It even shapes our culture and imagination. Countless myths, legends, and stories have been born from humanity's encounters with this shallow band of ocean. Ancient sailors feared monsters rising from the depths, while modern tourism markets it as a playground of snorkeling and sandy beaches. Our sense of the sea, historically and emotionally, has been tied almost entirely to what we can see and touch from the surface. Yet there is a subtle trick at play here. Because we spend so much time at the surface, we imagine it represents the whole. The ocean is so immense that even this outermost slice can feel endless. Sail across it in a small boat and you'll experience days or weeks with nothing but water in every direction. Fly over it and you'll see a moving patchwork of blue stretching for hours beneath you. The human scale, bound to our senses and technologies, is easily overwhelmed. To us, the surface looks infinite. But what lies beneath redefines infinity in a way we can scarcely imagine. The contrast between perception and reality becomes clear when you think about exploration. We have charted coastlines with accuracy. We've created shipping maps with precise coordinates and safe passages. We monitor surface temperatures from satellites. In some ways, the uppermost layer of the ocean is one of the best documented parts of our planet. And yet, when scientists try to look deeper, the certainty collapses. What we thought was well understood turns out to be precarious knowledge, balanced on a thin crust of observation. For example, large swathes of reef systems were once assumed stable, until bleaching events and climate shifts revealed how fragile they were. Fish populations thought inexhaustible have collapsed with overfishing. Currents assumed predictable are now wobbling under the stress of melting ice and rising temperatures. Even in the part of the ocean we believed we knew best, the surprises keep coming. It's worth pausing here to think about how the ocean looks from above, from the vantage point of satellites. Modern satellites can detect tiny changes in sea surface height, allowing scientists to infer what might be beneath, since underwater mountains and trenches tug gravitationally on the water above them. This gives us a global picture of ridges, basins, and seamounts. But the resolution is rough, often on the scale of kilometres. It's a bit like looking at a city from space. You can see the general outline of neighbourhoods, but none of the streets or buildings. This illusion of knowledge creates a strange situation. We think of the ocean as mapped, because we've drawn blue shapes on our atlases and traced shipping lanes across its surface. But in truth, we've mapped it in only the most general terms, with the detail missing almost everywhere. Another layer of misunderstanding comes from how we measure the ocean's health. Because most of what we track happens near the surface, we tend to assume the surface conditions reflect the whole. We measure water temperature, salinity, acidity, and life abundance in this upper band, and we build models based on that information. But deep below, conditions may differ dramatically, and we often don't know by how much. Think about it this way. It's as if you were asked to describe the life of a city by standing on one street corner for a day and watching what goes by. You might get a sense of the people, the traffic, the shops, and the weather. But you wouldn't know about the factories on the edge of town, the underground systems, or the neighbourhoods beyond your sight. Our understanding of the ocean is very much like that street corner view. Comprehensive at first glance, but shallow in reality. What's fascinating is how this shallow familiarity has shaped our myths. For centuries, humans treated the sea as a boundary, the edge of the known world. Maps labelled the uncharted waters with warnings, "Here be dragons." Sailors told tales of sea serpents, krakens, and mermaids. These stories weren't just superstition, they reflected the limits of knowledge. People filled the unknown with imagination, because the unknown itself was too vast to contemplate. Even now we project mystery onto the ocean in our stories. Films imagine colossal monsters rising from the depths. Novels picture lost cities hidden beneath the waves. Documentaries marvel at creatures discovered on the occasional deep-sea dive. The difference today is that our myths stand side by side with science, both acknowledging the same truth, that most of the ocean remains hidden from us. And yet, it's important to recognise that the ocean we think we know is not only a scientific challenge but a psychological one. The surface tricks us into believing we're close to understanding, when in fact we're still at the very beginning. When a person looks out at the sea, they feel they're seeing it in its entirety, but they're not. They're seeing the upper skin, a thin veil that hides everything beneath. This misperception can lead to overconfidence in how we manage it. We assume we can measure, regulate and exploit it with enough precision, only to be reminded again and again that the system is more complex than we imagined. The collapse of cod fisheries in the North Atlantic, the unexpected spread of invasive species through ballast water, the discovery of plastic pollution in remote ocean gyres. These are all signs that our apparent knowledge is far less complete than it appears. This is where the idea of impossibility begins to take root. If we struggle to fully understand even the surface zone, what hope do we have of comprehensively exploring the rest? The familiar, accessible ocean is already showing us the limits of our control and knowledge. And that's just the thinnest part. Beneath it lies an environment where conditions become exponentially more difficult, and where human senses and machines falter. It makes the challenge not just daunting, but endless, as if the more we discover, the further the horizon retreats. Even so, the surface ocean holds endless fascination. Watching waves crash or drift lazily can feel timeless, meditative. Currents move with patterns that seem eternal, even as they shift under the planet's changing climate. Storms gather, rise and fade with a kind of rhythm that ties us back to ancient sailors who once looked at the same patterns. The ocean we know, or think we know, is an anchor for human life in countless ways. It's where commerce moves, where cultures meet, where traditions are passed from generation to generation. That familiarity gives comfort, but it also disguises the greater mystery beneath. And it is that greater mystery that draws explorers and scientists again and again into the deeper layers. The recognition that the surface is only a mask, only the beginning of something larger, pushes us to look further, to question what lies beyond, to imagine what lives in the dark and what forces shape the floor beneath. Because if the surface already overwhelms us with its scale, what comes next is something that stretches our imagination and our tools to their breaking point. The ocean we think we know is only the introduction. Beyond it lies the real story, one where light vanishes, pressure builds, and the familiar rules begin to dissolve. That is where the impossibility of total exploration begins to reveal itself, and that is where our journey must continue, deeper into the water, toward the places where the ocean no longer feels like a friendly companion, but an entirely separate world with its own laws and rhythms. If the ocean's surface is the version we know best, the thin sunlit layer that gives us fish and trade routes and vacation postcards, then what lies beneath it is another world entirely. And calling it a world isn't exaggeration. The deeper ocean is so vast, so complex and so alien that it's almost misleading to think of it as part of the same planet. It's not simply more water. It's a space that obeys rules we barely understand, a realm that dwarfs our capacity to measure, explore and even imagine. And it's this depth, more than anything else, that makes the idea of fully exploring the ocean almost laughably beyond reach. The first thing that strikes you when you try to grasp the scale of the deep ocean is how poorly our everyday reference points prepare us for it. The average depth of the global ocean is about 3,688 metres. That's nearly 4 kilometres straight down, deeper than most mountains at all. The deepest known point, the Challenger Deep in the Mariana Trench, plunges to about 10,184 metres, nearly 11 kilometres below the surface. That's roughly the distance a commercial jet flies above the ground. Imagine flipping the atmosphere upside down and filling it with water. That's the kind of vertical scale we're talking about. And yet, even those numbers fail to capture the enormity of it, because they're just statistics. What matters is what they mean for exploration. Depth is not just a measurement of distance, it's a multiplication of difficulty. Every additional metre down adds layers of complexity. Pressure increases by 1 atmosphere every 10 metres, So by the time you're a kilometre deep, the water is pressing down with about 100 times the force you feel at the surface. At the bottom of the Mariana Trench, the pressure is over 1,000 times greater. It's the equivalent of having the weight of 50 jumbo jets bearing down on every square metre of a submersible's hull. This isn't just an engineering problem, it's a fundamental limitation. Materials behave differently under those conditions. Metal that seems indestructible on land can warp or crack. Electronics fail. Seals that hold under laboratory conditions begin to leak. The deeper you go, the harder it becomes to build something that will survive long enough to gather meaningful data, let alone return with it. The human body is even less equipped to handle such conditions. Most divers don't go deeper than about 40 metres without specialised equipment, and even with mixed gas systems and pressurised suits, human limits are reached long before the ocean's deepest zones. Beyond a few hundred metres, the crushing pressure makes direct human exploration nearly impossible without a submersible. That means much of our knowledge of the deep sea depends on machines, and machines face their own set of limitations. They are expensive to build, costly to operate, and vulnerable to failure. And unlike satellites or drones in space which operate in a near vacuum, underwater vehicles must constantly fight resistance. Water is dense, heavy, and full of currents. Propulsion takes enormous energy. Communication is slow and often unreliable because radio waves don't travel well underwater. Everything is harder in the deep. Then there's light, or rather the lack of it. Sunlight fades quickly in seawater, and by 200 metres it's already dim. Beyond 1,000, it's gone completely. The deep ocean exists in perpetual night, broken only by the faint glow of bioluminescent life and the occasional lamp of a passing robot. This changes everything about how exploration works. On land or in space, we rely heavily on visual data. Cameras, telescopes, and the human eye are all designed to work with light. But in the deep ocean, light is not an option. Instead, we rely on sonar, which sends out sound waves and measures their echoes to infer shapes and distances. Sonar works, but it's slow and imprecise. It's like trying to navigate a room by clapping and listening for the echoes. You get a general idea of where things are, but the finer details are lost. Our attempts to map the ocean floor reflect these limitations. Satellite altimetry, which infers seafloor topography from tiny variations in sea surface height, gives us a blurry picture, like a rough sketch of a landscape seen through fog. Ship-based sonar improves the resolution, but even that is slow and incomplete. A single research vessel can map only a narrow strip of seafloor as it moves, and mapping the entire ocean this way would take centuries of continuous work. As of now, only about 20% of the seafloor has been mapped in high detail. The rest remains a mystery, a vast, unmapped wilderness larger than the surface of Mars. And that's just the static picture. The ocean isn't a still, empty void. It's a dynamic, shifting environment full of motion and complexity. Currents flow in 3 dimensions, forming vast loops and eddies that stretch thousands of kilometres. Thermohaline circulation, driven by differences in temperature and salinity, connects surface waters to the deep in slow, planet-spanning conveyor belts that can take centuries to complete a single loop. Water masses mix, separate, and flow in ways that defy simple modelling. Exploring this depth isn't just about going down, it's about understanding a constantly moving, constantly changing space. The sheer size of that space is staggering. The ocean contains about 1.35 billion cubic kilometres of water. If you tried to explore it by sending a single autonomous robot that could scan 1 cubic kilometre per day, an impossible pace with today's technology, it would still take more than 3.5 million years to cover the entire volume. Of course, we can deploy more than one robot, but the scale of the challenge doesn't shrink much. Dozens, even hundreds of vehicles would still need tens of thousands of years. The point isn't the exact number, it's that the problem is orders of magnitude beyond what's practical. Even if technology improves dramatically, The combination of scale, pressure, darkness, and complexity means the ocean will likely remain largely unexplored for the foreseeable future. And yet, despite those challenges, we keep trying. Humans have a remarkable stubbornness when it comes to the unknown. We've built submersibles capable of diving to the ocean's deepest trenches. We've sent remotely operated vehicles to places no human could survive. We've deployed fleets of autonomous floats that drift through the water column, collecting data on temperature, salinity, and currents. Each of these efforts has expanded our understanding, but they've also revealed how much we still don't know. Every discovery seems to multiply the questions rather than answer them. Consider hydrothermal vents, for example. These underwater geysers were unknown until 1977, when scientists exploring the Galapagos Rift stumbled upon them by accident. The vents spew superheated water rich in minerals, creating chemical environments that support ecosystems unlike anything seen before. Entire communities of organisms thrive there without sunlight, relying on chemosynthesis instead of photosynthesis. This discovery revolutionized our understanding of life on Earth and raised profound questions about life's origins. And yet, hydrothermal vents exist in scattered, unpredictable locations, often in deep remote regions. We've mapped only a small fraction of them. How many remain undiscovered? What other surprises might they hold? We don't know, and given the size of the ocean, we might never know. The same goes for the seafloor itself. It's not a flat plain, but a rugged landscape of mountains, valleys, ridges, and trenches. The mid-ocean ridges, for example, form the longest mountain range on Earth, stretching more than 65,000 kilometers across the seafloor. Yet much of it has never been directly observed. There are underwater volcanoes erupting unseen, landslides carving new canyons, and tectonic processes reshaping the crust in ways we can only infer from distant measurements. Each time we send a vehicle down, we risk stumbling onto features no one knew existed, and each time we realize how incomplete our maps truly are. And then there's the life. The deeper we go, the stranger it gets. Creatures adapted to the crushing pressure and eternal darkness display forms and behaviors that defy expectations. Some produce their own light through bioluminescence, flashing signals to communicate or lure prey. Others drift like living balloons, gelatinous and transparent, feeding on particles that fall from above. Gigantic squid, once the stuff of sailors' tales, turn out to be real, though rarely seen. Entire ecosystems form around whale carcasses that sink to the seafloor, supporting diverse communities for decades in what scientists call whale falls. The deeper ocean isn't empty. It's alive in ways we're only beginning to glimpse, and for every creature we've catalogued, there may be dozens more we haven't. Some estimates suggest that 90% of species in the deep sea remain undiscovered. That means the ocean is not just a physical frontier, it's a biological one as well. All of this leads to an unsettling but fascinating truth. The deeper ocean is not just unknown because we haven't looked. It's unknown because it may be unknowable in any complete sense. Its scale, complexity, and constant change mean that by the time we finish exploring one part, another will have shifted. Currents will have rearranged the water. New geological features will have formed. Species will have evolved or migrated. Total exploration implies a static object, something that can be fully measured and catalogued. But the ocean is not static. It is a living, breathing, shifting system, and that makes the idea of exploring it completely something of a contradiction. This is perhaps why comparisons between the ocean and space are so common. Space feels infinite, but in some ways it's easier to explore. Space is mostly empty. There's no pressure to crush spacecraft, no dense medium to resist movement. Radio signals travel freely. Light travels unimpeded. In the deep ocean, none of that is true. Every meter forward is a fight. Every signal is muffled. Every instrument is pushed to its limits. That's why, despite having sent probes beyond the solar system, we still struggle to map the seafloor of our own planet. The irony isn't lost on oceanographers. We know more about the surfaces of other worlds than we do about the bottom of our own seas. And yet, even with all these barriers, exploration continues, driven by a mix of curiosity, necessity, and hope. We need to understand the deep ocean because it plays a crucial role in Earth's climate system. Deep currents store and transport heat and carbon, regulating global temperatures. Deep ecosystems recycle nutrients that support surface life. Deep geological processes shape the crust and influence seismic activity. Ignoring the deep ocean isn't an option, but fully exploring it may be beyond our reach. That tension between the need to know and the impossibility of knowing everything is what makes ocean exploration such a compelling human endeavour. There's another dimension to this too, one that's less about physics and more about perspective. The deeper we go, the more we realise how limited our ideas about exploration really are. We tend to think of exploration as a process of filling in blanks on a map, of cataloguing and classifying until nothing is unknown. But the deep ocean resists that approach. It's too vast, too dynamic, too full of surprises. It doesn't lend itself to neat categories or definitive maps. It demands a different kind of exploration, one that accepts uncertainty as part of the process. Maybe the point isn't to know everything, but to keep learning, knowing full well that the learning will never end. And that brings us back to the heart of why exploring the whole ocean is impossible. It's not just a matter of technology or funding or political will, though those things matter. It's that the ocean itself is a moving target, a vast and shifting system that defies finality. Even if we built machines that could withstand the pressure, like the darkness, and map every contour, by the time they finished, the ocean would have changed. New layers of sediment would have shifted, species would have moved, chemical gradients would have evolved. The moment you think you've captured it, it slips away, changed into something else. But maybe that's what makes it worth exploring at all. The ocean's depth is a reminder that some mysteries are not meant to be solved but engaged with. They exist not to be conquered but to keep us curious, to keep us searching. The impossibility of exploring the whole ocean isn't a failure, it's a feature. It means there will always be something left to discover, always another dive, another question, another piece of the puzzle waiting in the dark. And as we continue deeper into this story, that darkness will only grow more fascinating, more complex and more humbling, because the deeper ocean is only one part of the challenge. Its terrain, rugged, shifting and full of hidden wonders, adds another layer to the impossibility, one that makes even the idea of a complete map feel like a dream slipping out of reach. The deeper you travel beneath the waves, the more the world you know begins to fall away. It doesn't happen all at once. It happens gradually, almost imperceptibly, as though the ocean is peeling back familiar layers and replacing them with something entirely new. At first, the water around you is still bright, still filled with the play of sunlight scattered by waves above. You can still see shapes and colours, still recognise the shimmer of fish and the sway of seaweed. But with every metre you descend, the light fades a little more. Reds disappear first, then oranges and yellows, until all that remains are shades of blue and violet. Go deeper still, and even those vanish, replaced by a darkness so complete it feels less like the absence of light, and more like the presence of something else entirely. Down here, light doesn't belong. Beyond about 1,000 metres, the ocean is a world of perpetual night. Sunlight never reaches this far, no matter how bright the day above. It is a realm defined not by vision but by pressure, temperature, and the slow, constant movement of water. This is the midnight zone, a region that covers more than half of the planet's surface and yet remains almost entirely beyond human experience. It's difficult to convey just how different this world is. The darkness is not the same as night on land. On land, even the darkest night carries some trace of light, whether from stars, the moon, or distant cities. Here, there is none. You could shine the most powerful spotlight humanity has built, and it would reach only a short distance before the water swallowed it whole. In this darkness, the familiar rules of life and physics bend into new shapes. Temperature plummets to near freezing. Pressure builds relentlessly. Sound behaves differently. The water itself is heavier, denser, layered in subtle gradients that shift and flow. Everything here exists under conditions that would be lethal closer to the surface, and yet this world is not empty. On the contrary, it is teeming with life. Life that has adapted not just to survive, but to thrive in an environment that would crush, freeze, and disorient almost anything from the world above. The creatures that inhabit this darkness are unlike anything most people ever see. Many are fragile and translucent, built to float effortlessly in the dense water. Some produce their own light through bioluminescence, a chemical reaction that turns the darkness into a stage for flickers and flashes, pulses and glows. These living lights are more than just decoration. They are tools for survival, lures for prey, warnings for predators, signals for mates. In a world where eyes are often useless, light becomes language. Some animals use it as camouflage, counter-illuminating their undersides to blend with the faint glow from above. Others use it to confuse predators, releasing bursts of light like underwater flashbangs. There are creatures that wave luminous lures like fishing lines, and others that light up their entire bodies in elaborate displays. But light is not the only adaptation here. Many deep-sea animals rely on senses we barely understand. Some detect minute changes in pressure or vibrations, allowing them to sense movement in the water long before they see or are seen. Others have evolved enormous eyes, capable of capturing the faintest glimmers of bioluminescence. Some have dispensed with vision entirely, navigating the dark with chemical or mechanical cues. Evolution has sculpted them into forms that seem bizarre by surface standards. Long, ribbon-like bodies that undulate through the water, jaws filled with needle-like teeth to trap scarce prey. Gelatinous forms that conserve energy by drifting rather than swimming. And then there are the giants. Down here, size follows different rules. Creatures like the giant squid grow to lengths of over 12 meters, lurking in the darkness with eyes the size of dinner plates, among the largest eyes in the animal kingdom. These massive eyes aren't a luxury, they're a necessity. They allow the squid to detect faint flashes of light from potential prey or approaching predators, like the elusive sperm whales that dive deep to hunt them. Encounters between these titans happen in darkness so complete that they've never been observed directly. What we know of them comes from scars on whale skin, from remains found in stomachs, from glimpses on deep-sea cameras, fragments of a hidden war playing out far below the surface. For humans, this darkness is a formidable barrier. Our entire evolutionary history has taken place in a world defined by light. Our eyes, our tools, our ways of perceiving and understanding rely on it. In the deep ocean, that reliance becomes a weakness. Cameras struggle to capture meaningful images without artificial lighting, and artificial lighting itself can disrupt the very environments we're trying to study. Some deep-sea species are sensitive to even the faintest illumination. Others are drawn to it, altering their behavior in ways that make observation difficult. It's a paradox of exploration. To see this world, we must change it. Sound offers an alternative, but it too comes with complications. Because light fades quickly in water, sonar is often our best tool for seeing in the deep. By sending out sound waves and listening for their echoes, scientists can map terrain, detect objects, and even track animals. But sonar has its limits. It provides only outlines, not details. It struggles with small, soft-bodied creatures, and like light, it can alter behavior, startling animals or driving them away. The deeper we go, the more we realize that our tools, designed for the world above, are blunt instruments here. Even communication becomes a challenge. Radio waves, which carry our signals through air and space, are almost useless underwater. They attenuate rapidly, losing strength after only a short distance. This means that deep-sea vehicles often rely on acoustic signals, which are much slower and carry far less data. A simple instruction that would take milliseconds to send to a satellite might take seconds or minutes to reach a submersible. Real-time control becomes difficult, sometimes impossible. As a result, many deep-sea missions depend on autonomous systems, robots that must make decisions on their own, far from direct human oversight. That autonomy is both a strength and a vulnerability. It allows exploration where humans cannot go, but it also means that if something goes wrong, help is often hours or days away. The darkness hides not only life but landscape. The seafloor here is a place of extremes. Vast plains stretch for thousands of kilometers, covered in fine sediment that drifts down from above like underwater snow. Elsewhere, jagged ridges rise like mountain ranges, formed by the slow spreading of tectonic plates. Deep trenches plunge into the crust, deeper than any canyon on land. Hydrothermal vents spew mineral-rich water heated by magma beneath the seafloor, creating oases of chemical energy in the cold darkness. Cold seeps leak methane and hydrogen sulfide, supporting yet more unique ecosystems. This landscape is as varied and dramatic as anything on the continents, but we've seen only a tiny fraction of it. What little we have seen has already transformed our understanding of the planet. Before hydrothermal vents were discovered, scientists believed that all life on Earth ultimately depended on sunlight. The ecosystems clustered around those vents proved otherwise. Here, bacteria use chemicals from the vent fluids to produce energy, forming the base of a food chain that includes giant tube worms, clams, and crabs. It was a revelation that reshaped not just marine biology, but our understanding of life itself, raising new questions about how life might arise in dark, energy-rich environments elsewhere in the universe. Yet hydrothermal vents are just one example. The deep ocean is full of features and processes we barely understand, and many we likely don't even know exist. Exploring this world is slow, painstaking work. Deploying a deep-sea submersible takes hours just to descend to its destination. Once there, its range and speed are limited. It can examine only a small area before it must return to the surface. Each dive is expensive, requiring ships, crews, and careful planning. Weather, currents, and mechanical failures can delay or cancel missions. And because the ocean is so vast, each successful dive covers only a tiny fraction of what's out there. Imagine trying to explore an entire continent by lowering a single elevator shaft into it. That's roughly the scale of the challenge. Even when we do reach these depths, the data we collect is incomplete. Cameras capture only what's directly in front of them. Sonar maps large features but misses small ones. Water samples represent a single moment in time, but the ocean is constantly changing. Conditions can vary dramatically from one dive to the next, or even from 1 hour to the next. What we see may not be representative of what's typical, and what's typical may change before we have a chance to return. The deep ocean is not a static environment waiting to be catalogued. It's a living system in constant motion, and that motion isn't limited to water. The seafloor itself shifts and evolves. Earthquakes reshape trenches. Volcanic eruptions create new seamounts. Landslides send avalanches of sediment racing across the abyssal plains. These events can alter entire ecosystems, burying some and creating new ones. They can also erase or obscure the very features we're trying to study. A vent field mapped 1 year might look entirely different a decade later. A canyon explored in one expedition might collapse before the next. This dynamic nature makes comprehensive exploration even harder. By the time we think we've mapped something, it may already have changed. One of the most profound aspects of this darkness is how little of it we've actually touched. It's estimated that humans have directly observed less than 0.05% of the deep ocean. That's not a typo. Less than 1/20th of 1%. The rest remains unseen, unknown, and perhaps unknowable. Every deep-sea mission, no matter how advanced, is a glimpse through a keyhole into a vast, dark cathedral. And every glimpse reveals how much more there is beyond our reach. It's humbling, and it's a big part of why the idea of exploring the whole ocean is so implausible. We're not just dealing with scale, we're dealing with a level of inaccessibility that fundamentally defies our tools and senses. Yet for all its challenges, this darkness is not hostile, it is indifferent. It doesn't resist us actively, it simply is. The pressure, the cold, the lack of light, these are not barriers built to keep us out. They are the natural state of a world that existed long before we arrived and will continue long after we're gone. In that sense, the deep ocean is a reminder of our place in the universe. It shows us that not everything is made to accommodate us, that not all worlds are meant to be easily understood or conquered. And perhaps that's part of the reason it fascinates us so deeply. It's worth remembering too that darkness is not just a physical condition but a metaphor for ignorance. When we speak of the deep ocean as a world of darkness, we're also speaking of how little we know, and that ignorance is profound. Scientists estimate that there could be tens of millions of species living in the ocean, many of them in the deep. Most have never been named, let alone studied. Entire ecosystems could exist beyond our awareness. Geological features could be forming right now, unseen. Chemical processes could be unfolding that might one day lead to breakthroughs in medicine, energy, or materials science. The darkness hides not just what is, but what could be. And that is perhaps the most compelling reason we keep returning. Despite the darkness, despite the pressure, despite the limitations of our technology, we are drawn to the deep. Every time a submersible descends, it has the potential to rewrite what we know. Every image from the abyss, every water sample, every sonar map is a piece of a puzzle we're still struggling to understand, and with each piece the picture becomes more complex, not less. The deeper we go, the more we realize how far we are from understanding the whole. This is why the ocean remains one of the last great frontiers, not because we haven't tried to explore it, but because it resists finality. Its darkness is not just a physical barrier, but a conceptual one. It forces us to rethink what exploration means. It demands patience, humility, and acceptance of uncertainty. And it shows us that some mysteries are not meant to be solved once and for all, but revisited again and again, each time revealing a little more and reminding us how much remains unknown. The darkness below is not the end of the story. It's the setting in which the rest of the story unfolds. Because within that darkness, beneath those crushing pressures and shifting landscapes, lies a terrain as intricate and challenging as any mountain range or desert on land. It is a terrain that stretches for thousands of kilometers, hides secrets in its folds and reshapes itself in silence. It is the ocean floor, the vast rugged foundation of this hidden world, and it presents its own set of obstacles, each one a reason why exploring the whole ocean might remain beyond our reach. Pressure is something we rarely think about in our daily lives, yet it is always present. At sea level, the weight of Earth's atmosphere presses down on every square centimetre of your body with about 1 kilogram of force. You don't feel it because the fluids inside you push back with equal strength, and because evolution has shaped your body to exist comfortably under that constant weight. But pressure is a subtle and relentless force, and as you descend into the ocean, it rises with astonishing speed. Every 10 meters down adds another atmosphere, another full weight of air stacked on top of you. At 100 meters, the pressure is 10 times greater than what you feel on land. At 1,000, it's 100 times greater. And at the bottom of the Mariana Trench, nearly 11 kilometers below the surface, the pressure is more than 1,000 times what your body is built to endure. To imagine what that means, consider this. Every square inch of an object at the bottom of the trench is being squeezed by more than 8 tons of water. That's roughly the weight of a fully loaded truck pressing on an area the size of a postage stamp. Multiply that across the entire surface of a submersible, and you begin to understand why deep-sea engineering is so difficult. Even the smallest flaw in a vessel's hull, a microscopic crack, an imperfect weld, can become catastrophic under that kind of force. The water does not give second chances. It doesn't rush in, it slams in. When pressure breaches a barrier, it does so with explosive violence, crushing and imploding everything inside in an instant. For humans, this means direct exploration of the deep ocean is almost entirely off limits. Divers can only descend so far before the pressure becomes too great for their bodies to withstand. Even with advanced breathing mixtures and pressurized suits, human limits are reached long before the deep ocean truly begins. The world record for a human free dive is just over 200 meters, and even that is a fleeting visit measured in minutes. With scuba gear, divers rarely go beyond 40 to 60 meters for safety. The deepest recorded dive with specialized equipment is just over 330 meters. Beyond that, human physiology simply can't cope. Lungs collapse, nitrogen dissolves into the blood, and oxygen becomes toxic. The deeper layers of the ocean are a realm from which we are excluded by the basic limits of our biology. That's why machines have become our eyes and ears in the deep. Submersibles, remotely operated vehicles, and autonomous underwater drones do what humans cannot. They survive where pressure would crush a person into pulp. But even these marvels of engineering face daunting challenges. A deep-sea submersible must be built like a fortress, with thick titanium or steel hulls designed to withstand the immense forces pressing on them. These hulls are often spherical, the strongest shape for resisting uniform pressure. But strength comes at a cost. The thicker and heavier a hull, the harder it is to build, launch and maneuver. And the deeper you want to go, the thicker and heavier it must be. At a certain point, the engineering becomes impractical, the cost astronomical. Consider the bathyscaphe Trieste, which in 1960 carried Jacques Picard and Don Walsh to the bottom of the Challenger Deep. Its pressure sphere had walls nearly 13 centimeters thick, and even so, the immense pressure caused a window to crack during the descent. The mission was a triumph, but it was also a demonstration of how unforgiving the deep ocean can be. It would be more than half a century before another crewed vehicle, James Cameron's Deep-Sea Challenger, returned to the same depth. And that gap wasn't due to a lack of interest. It was because building something capable of surviving that pressure safely and reliably is incredibly difficult and expensive. Even unmanned vehicles face similar obstacles. Pressure-resistant housings, pressure-tolerant electronics, and robust seals all add weight and complexity. The deeper a vehicle is designed to go, the more costly it becomes, both in terms of money and energy. Batteries must work under conditions that strain their chemistry. Sensors must function reliably in crushing environments. Every component must be tested and retested, because failure is often catastrophic and irretrievable. A submersible that implodes at depth is unlikely ever to be recovered. Pressure doesn't just threaten machines, it also changes the way materials behave. Metals become more brittle, plastics deform. Glass, often used for viewports, must be carefully shaped and treated to avoid shattering. Even the water itself behaves differently. At great depth, it is denser and more viscous, and it exerts forces that can subtly alter the performance of instruments and vehicles. Designing for these conditions is as much about understanding the behavior of materials under pressure as it is about resisting the pressure itself. The immense force also complicates the task of collecting samples. A water sample taken from several kilometers down is under enormous pressure when it's collected. Bring it to the surface too quickly, and gases dissolved under those conditions will bubble out, changing the sample's chemistry before it can be studied. Biological specimens face similar problems. Deep-sea creatures often cannot survive the transition to surface pressure. Their bodies, adapted to crushing depths, expand or even disintegrate when brought up too quickly. This makes it difficult to study them alive and in their natural state. Specialized pressure-retaining containers can help, but they are expensive and cumbersome, and they limit the amount of material that can be collected. These challenges explain why so much of the deep ocean remains unexplored. It's not that we lack curiosity or even the basic technology to reach those depths. We've done it before. It's that doing so is so resource-intensive, risky, and technically demanding that it's impossible to do at scale. A handful of dives scattered across decades barely scratch the surface of what's out there. And because the ocean is so vast, each dive is a tiny point in a massive three-dimensional volume. It's like trying to understand a continent by drilling a few narrow shafts into the ground. The information you get is valuable, but it's far from complete. Pressure also affects how long we can explore once we reach the deep. The deeper a submersible goes, the longer it takes to descend and ascend. A trip to the bottom of the Mariana Trench can take more than 4 hours each way. That leaves only a few hours at depth before the vehicle must begin its slow climb back to the surface. The deeper the dive, the more of the mission is spent simply travelling, and the less time is available for actual exploration. This is another reason why most deep-sea research focuses on relatively accessible depths, 1,000 or 2,000 metres rather than 10,000. The deeper you go, the more difficult everything becomes. There's also the problem of cumulative stress. Every dive subjects a submersible to immense pressure cycles. Over time, these stresses can cause microscopic cracks or fatigue in the hull and components, even if they aren't immediately visible. Engineers must constantly inspect, maintain, and sometimes retire vehicles long before their mechanical parts wear out. This adds another layer of cost and complexity, one that makes frequent routine deep dives impractical. The challenge of pressure extends beyond engineering and biology. It shapes how we think about exploration itself. On land, exploration often means moving quickly and covering large areas. We climb mountains, cross deserts, map landscapes. In the deep ocean, pressure slows everything down. Vehicles move cautiously. Dives are planned meticulously. Every step is deliberate because mistakes can be fatal to machines and impossible to fix once they occur. Exploration here is not a sprint but a crawl, a slow and careful process that yields its secrets grudgingly. And even when we succeed, pressure still limits what we can do. Instruments that work perfectly at the surface may fail at depth. Cameras may crack. Robotic arms may seize. Communication links may falter. The deeper we go, the more likely something will break. And when it does, repairs are often impossible without bringing the entire vehicle back to the surface. Each failure means days, weeks, or months of lost time and effort. Each repair adds cost. Each redesign must account for even greater pressures. It is a cycle that repeats again and again, a reminder that the ocean's crushing embrace is not something we can simply design our way around. Pressure also affects the very structure of the ocean itself. At great depths, water becomes so compressed that its density increases significantly. This affects how sound travels, how currents flow, and how heat moves. It creates layers within the water column, each with its own physical properties. These layers can act as barriers, trapping heat, nutrients, or even organisms. They complicate navigation and make it difficult to model how the ocean behaves as a system. Pressure is not just a challenge for explorers, it is a fundamental force shaping the ocean's structure and dynamics. The way pressure shapes life is perhaps the most profound reminder of how alien the deep ocean really is. Organisms here have evolved extraordinary adaptations to survive. Some have flexible cell membranes that resist compression. Others produce special proteins that prevent their enzymes from denaturing under pressure. Some have skeletons made of cartilage rather than bone, which can bend without breaking. Many are slow-growing and long-lived, conserving energy in an environment where movement is costly. These adaptations are so specialised that they often make survival at surface pressures impossible. A fish from the abyss may literally explode if brought up too quickly, its internal gases expanding violently as the pressure drops. These differences highlight a key point. The deep ocean is not just a deeper version of the world we know. It is a fundamentally different environment, one where pressure shapes every aspect of existence. It is as distinct from the surface ocean as the surface ocean is from dry land, and that means that exploring it is not just a matter of going deeper. It is a matter of entering a new world with new rules, where everything we take for granted must be rethought. The problem is that our tools and methods are still rooted in the world above. We build machines with materials and designs that work well in air or shallow water, and then we try to adapt them for the deep. But the deep ocean demands a different approach, one that accounts for the relentless force pressing in from all sides. Engineers are experimenting with new materials like advanced ceramics and composites that might offer strength without excessive weight. They're exploring pressure-tolerant electronics that don't need heavy housings. They're even developing soft robots modelled after deep-sea creatures, designed to bend and flex rather than resist. These innovations are promising, but they are still in their infancy, and even if they succeed, they will not eliminate the fundamental problem. The deeper we go, the greater the pressure, and the harder it is to work there. Pressure also imposes limits on the scale of exploration. Large vehicles require enormous amounts of energy to descend and ascend, and they're costly to operate. Smaller vehicles can be deployed more easily, but they're often less capable and more vulnerable. Balancing these trade-offs is a constant challenge. Do you build a few large, robust submersibles capable of reaching the deepest trenches, or many smaller ones that can explore more areas but not as deeply? Each choice has consequences, and none offers a complete solution. It's tempting to imagine that future technology will solve these problems, that one day we'll have materials strong enough, power sources dense enough, and systems reliable enough to make deep exploration routine. And perhaps we will. But even then, pressure will remain a fundamental fact of the ocean. It cannot be eliminated or ignored. It is built into the nature of water itself, into the weight of the column above. It is a constant reminder that the ocean is not just vast but heavy, that every metre of depth adds another layer of challenge. In a way, pressure is the ocean's signature. It is what makes the deep so alien, what shapes its landscapes, its life, and its mysteries. And it is one of the main reasons why exploring the whole ocean is impossible. It is not a barrier we can tear down or a problem we can solve once and for all. It is an ever-present force, a fact of physics that will always shape what we can and cannot do. Yet pressure is not the only obstacle. Even if we could build machines that laughed in the face of 1,000 atmospheres, we would still face a world far more complex and unpredictable than we are used to. Because beneath the crushing weight of the water lies a seafloor unlike anything we see on land. A landscape of mountains and trenches, volcanoes and plains, carved and reshaped by forces that never sleep. And if pressure is the ocean's signature, that landscape is its hidden handwriting, a record of Earth's restless geology scrawled across a realm we've barely begun to read. When most people picture the bottom of the ocean, they imagine a flat, featureless plain, a smooth, endless expanse of mud stretching away into the dark. It's an understandable image, shaped by decades of illustrations and the fact that we almost never see it with our own eyes. But the reality is far more complicated. The seafloor is not a blank canvas. It is one of the most rugged, dynamic and varied landscapes on Earth. It is a labyrinth of ridges, trenches, mountains, plains and volcanoes, carved and reshaped by geological forces that have been at work for hundreds of millions of years. If the deep ocean is another world, then its floor is an alien continent, and that complexity is one of the main reasons why exploring it fully may be forever beyond our reach. The most striking feature of the ocean floor is its sheer diversity. Just as the surface of the Earth contains mountains, valleys, rivers and deserts, the seafloor is a patchwork of landscapes, each with its own characteristics and challenges. Some areas are dominated by vast abyssal plains, flat expanses of fine sediment that stretch for thousands of kilometres. Others are broken by towering seamounts, underwater mountains that rise from the depths like islands without summits. There are deep trenches, narrow and impossibly steep, that slice into the crust and plunge deeper than Mount Everest is tall. There are mid-ocean ridges, massive underwater mountain chains formed by the slow spreading of tectonic plates, and scattered among all of these are volcanic vents, submarine canyons, sediment drifts, and countless smaller features, many of which we don't even have names for yet. The mid-ocean ridges alone are enough to stagger the imagination. Together they form the longest mountain range on Earth, more than 65,000 kilometers long, about 1.5 times the circumference of the planet. These ridges wind their way through all the world's oceans, rising as much as 3 kilometers above the surrounding seafloor. They are the birthplace of new crust, where molten rock wells up from the mantle and pushes the tectonic plates apart. Along their length, hydrothermal vents spew superheated water and minerals, creating oases of life in the darkness. But despite their importance, most of these ridges remain unexplored. In some places, we have little more than satellite data showing their rough outlines. Detailed maps exist for only a tiny fraction of their length. Then there are the trenches, the deepest places on Earth. These narrow arc-shaped depressions form where one tectonic plate is forced beneath another, plunging into the mantle. The Mariana Trench is the most famous, but there are many others. The Tonga Trench, the Kuril-Kamchatka Trench, the Philippine Trench. Each is a place of extremes, where pressure exceeds 1,000 atmospheres and temperatures hover just above freezing. These trenches are difficult to reach and even harder to study. Their steep walls and narrow shapes make navigation challenging, and their great depth means that every dive requires hours of descent and ascent. As a result, many trenches have been visited only once or twice, if at all. Some have never been explored directly. Even the supposedly flat abyssal plains are not as simple as they appear. They're covered in fine sediment that drifts down from above over millions of years, creating a soft, uniform surface. But beneath that surface lie layers of rock and ancient lava flows, shaped by tectonic and volcanic forces. The plains are dotted with features called abyssal hills, small rounded rises that can be hundreds of meters tall and stretch for kilometers. There are thousands of them, perhaps millions, scattered across the ocean floor. Most remain unmapped, their shapes and locations inferred only from coarse satellite data. And then there are the seamounts, an estimated 100,000 of them, rising at least a kilometre above the sea floor, with many more smaller ones besides. Some are extinct volcanoes, others are still active, venting heat and chemicals into the water. They form islands of biodiversity, home to unique ecosystems that often exist nowhere else on Earth. This rugged terrain presents enormous challenges for exploration. Mapping it with precision requires sonar surveys conducted from ships or submersibles, and those surveys are slow. A research vessel equipped with modern multi-beam sonar can map a strip of seafloor a few kilometers wide as it moves. But even at that pace, mapping the entire ocean would take centuries. As of today, less than a quarter of the seafloor has been mapped in high resolution. The rest remains a blur of approximations, with features that may be off by hundreds of meters in height or location. It's not that we don't want to map it, it's that the scale of the task dwarfs our capacity. Terrain also complicates the task of navigation. Deep-sea vehicles rely on sonar and inertial guidance rather than GPS, which doesn't penetrate water. In rugged environments, sonar signals can bounce unpredictably, creating echoes and false readings. Narrow trenches can trap sound waves, distorting the data. Steep slopes and overhangs can hide features from view, much as a mountain ridge can block a valley from sight. And because water is not uniform, it varies in temperature, salinity, and density. Sound travels at different speeds in different layers, bending and refracting as it goes. All of this makes accurate mapping and navigation a constant challenge. The terrain isn't just complex, it's constantly changing. Tectonic plates move, albeit slowly, shifting the positions of ridges and trenches. Earthquakes reshape the seafloor in sudden bursts, triggering landslides that can bury entire regions under kilometers of sediment. Submarine volcanoes erupt, building new seamounts or expanding existing ones. Sediment flows cascade down continental slopes, carving canyons and depositing vast fans of material on the abyssal plains. Even at smaller scales, the seafloor is dynamic. Currents move sediment around, eroding some areas and building up others. Hydrothermal vents appear and disappear as geological activity shifts. Features that exist today may look very different a decade from now. This dynamic nature makes comprehensive mapping not just difficult, but fundamentally elusive. Even if we somehow mapped the entire seafloor tomorrow, the map would be outdated almost immediately. It's not that the terrain changes overnight, though it sometimes does, but that it is always changing, always evolving. Exploration implies a fixed object to explore, but the ocean floor is not fixed. It is alive with geological activity, constantly reshaping itself in ways both subtle and dramatic. That means that total exploration is not a one-time task, but an ongoing process, one that could never truly be finished. The complexity of the terrain also influences the distribution of life in the deep ocean. Seamounts, for example, act as islands of biodiversity, providing hard surfaces for corals and sponges to attach to, and creating upwellings that bring nutrients from the depths. Trenches, by contrast, are often sparsely populated, though some harbour specialised communities adapted to the crushing pressure and scarce food. Hydrothermal vents support entire ecosystems based on chemosynthesis, while abyssal plains rely on a slow rain of organic particles falling from above. This patchwork of habitats means that exploring the deep ocean is not just a matter of mapping physical features. It also means understanding the biological and chemical systems that are shaped by those features. And because those systems are so varied and so dependent on local conditions, each new area we explore brings new surprises. One of the most striking examples of how terrain shapes life is the discovery of cold seeps, places where hydrocarbons like methane and hydrogen sulfide leak from the seafloor. These seeps create chemical-rich environments that support unique ecosystems, including bacteria that metabolize the chemicals in larger organisms like clams and tube worms that depend on those bacteria. Cold seeps were unknown until the 1980s, and they continue to surprise scientists with their diversity and complexity. They are often found in association with specific geological features, such as faults or sediment layers, and locating them requires detailed knowledge of the seafloor structure. But because much of that structure is still unmapped, many seeps likely remain undiscovered. The labyrinthine nature of the seafloor also hides potential hazards. Submarine landslides can generate tsunamis, even when they occur far from shore. Volcanic eruptions can release plumes of ash and gas that affect water chemistry and marine life over vast areas. Earthquakes can trigger changes in currents or disrupt ecosystems. Understanding these processes is crucial for everything from hazard prediction to resource management, but our lack of detailed knowledge about the seafloor makes that understanding incomplete. We know these events happen, but we often don't know where or when, and sometimes we don't even know they've occurred until we see their effects elsewhere. Technology has improved our ability to study this complex terrain, but it has not eliminated the challenges. Autonomous underwater vehicles, AUVs, can map small areas in detail, flying close to the seafloor and capturing high-resolution sonar images. Remotely operated vehicles, ROVs, can investigate specific features, collecting samples and taking close-up video. But these tools are limited in range and endurance. AUVs typically operate for a day or two before they must be recovered and recharged. ROVs require a ship and crew on the surface, making them expensive and logistically challenging to deploy. And because they move slowly, often just a few kilometers per hour, covering large areas is impractical. At best, we can explore small pieces of the puzzle, but stitching those pieces together into a complete picture remains beyond our capabilities. Even satellite mapping, which offers a global perspective, has limitations. Satellites cannot see the seafloor directly. They infer its shape from slight variations in sea surface height caused by gravity. This method can reveal large features like ridges and trenches, but it misses smaller structures and provides only a rough approximation of depth. It's a bit like trying to map a mountain range by measuring the thickness of the air above it. You get the general outline, but not the details. For exploration that requires precision, satellite data is just the starting point, not the final answer. Another layer of complexity is added by the interaction between terrain and water. The shape of the seafloor influences how currents flow, and those currents in turn shape the terrain. Seamounts deflect water upward, creating localized upwellings. Trenches channel deep currents, funneling cold, nutrient-rich water across great distances. Ridges steer the flow of entire ocean basins. These interactions create feedback loops that affect everything from nutrient distribution to climate. Understanding them requires detailed knowledge of both the terrain and the water that moves over it, and because both are complex and constantly changing, that understanding is difficult to achieve. The terrain also poses challenges for human activities beyond exploration. Submarine cables, which carry most of the world's internet traffic, must be carefully routed to avoid steep slopes and unstable areas. Deep-sea mining, which is still in its infancy, must contend with rugged landscapes and uncertain geological conditions. Even basic tasks like anchoring instruments or building observation platforms become complicated when the ground beneath them is uneven, shifting, and poorly mapped. The ocean floor is not a simple surface on which we can operate. It is a dynamic environment that demands constant adaptation. All of these factors contribute to the impossibility of fully exploring the ocean. The terrain is too vast, too varied, too dynamic to be mapped and studied in its entirety. Even if we had unlimited time and resources, the seafloor would change faster than we could chart it. New features would form, old ones would disappear, and our maps would always lag behind reality. The labyrinth is not just physical, it is temporal. It is a moving target that cannot be pinned down. And yet, despite these challenges, exploration continues. Every new map, every new dive, every new discovery adds a piece to the puzzle. We learn more about how the seafloor shapes life, how it influences currents, how it records the history of our planet. We discover new ecosystems, new geological processes, new insights into the workings of Earth itself. But each discovery also reminds us how much we still don't know. For every ridge we map, there are dozens more unseen. For every vent we study, there are countless others hidden in the dark. The labyrinth stretches on, vast and unending. Perhaps that's what makes it so compelling. The seafloor's complexity is not just an obstacle. It's part of what makes the ocean such a rich and fascinating place. Its hidden valleys and towering mountains, its shifting plains and explosive volcanoes, its deep, shadowed trenches. All of these are chapters in a story that is still being written. We may never read the whole story, but each glimpse draws us deeper, each discovery beckons us onward. And as we push further into the labyrinth, we find not just more terrain, but more life, more complexity, more wonder than we ever imagined. But the terrain is only part of the problem. Even if we could map every ridge and trench, even if we could trace every current and sample every vent, the ocean would still slip beyond our grasp in another way. Because it is not static. It is alive with motion. Its waters shifting and swirling in patterns that defy easy prediction. And that ever-changing nature, that restless, ceaseless movement, adds yet another layer to the impossibility of exploring the whole ocean. For all the complexity of the ocean's depths, the darkness, the pressure, the terrain, perhaps the most human obstacle standing between us and full exploration is one we've built ourselves. It's not just that the ocean is vast or hostile, it's that the machines we rely on to explore it, though impressive by any standard, are bound by limitations that mirror our own. They are, after all, our creations, built with materials we can produce, powered by energy sources we can harness, and controlled by systems we can understand. and while they have extended our reach far beyond what our bodies could ever achieve, they remain clumsy and fragile tools in a realm that demands precision, endurance, and resilience beyond anything we've yet mastered. Machines are the only reason we know anything about the deep ocean at all. Without them, the crushing pressures and freezing temperatures would keep us locked forever at the surface, peering down into darkness we could never enter. Over the past century, human ingenuity has produced an array of devices designed to push deeper and stay longer than any diver could dream. Bathyscaphs like Trieste carried explorers to the deepest trenches decades before modern computers existed. Remotely operated vehicles, or ROVs, now dive thousands of meters below the surface, transmitting high-definition video from places no human eye has seen. Autonomous underwater vehicles, or AUVs, drift silently through the abyss, mapping terrain and measuring water properties. These machines have transformed the unknown into the partially known, and yet, despite their remarkable capabilities, they are still far from what the ocean demands. Start with the basics. Power. On land, energy is easy to supply. Machines can plug into grids, refuel at stations, recharge with sunlight. In space, solar panels can operate almost indefinitely in the vacuum. But in the deep ocean, none of those options work. Sunlight doesn't penetrate far below the surface, and radio waves can't deliver energy through water. Most underwater vehicles rely on onboard batteries, which are heavy, expensive, and limited. Even the most advanced lithium-ion systems can only power a submersible for a matter of hours or days before it must return to the surface. That means exploration is almost always a series of short missions, each constrained by the finite energy the vehicle can carry. The deeper the dive, the more power is needed just to descend and ascend, leaving less for exploration once it arrives. Cables can supply power from the surface, but they come with their own problems. A tethered ROV is limited in range and mobility, forced to trail its lifeline like an umbilical cord. The deeper it goes, the longer and heavier the cable must be, adding drag and complicating manoeuvring. The cable itself can snag on seafloor features, break under tension, or interfere with delicate operations. And while tethered systems are common for shallow and mid-depth missions, they become impractical in the deepest parts of the ocean, where kilometers of cable would be required. That's why many deep diving vehicles must be autonomous, and autonomy introduces another set of challenges. Autonomous vehicles operate without direct human control, guided instead by pre-programmed instructions and onboard decision-making algorithms. This allows them to work where communication is slow or impossible, but it also limits their flexibility. A human pilot can react instantly to unexpected discoveries, adjusting course to investigate an unusual feature or pursue a curious creature. A robot cannot, at least not yet. Its programming dictates its behaviour, and while artificial intelligence is improving, it's still far from matching human intuition and adaptability. If an autonomous vehicle encounters something truly unexpected, it may not recognise its importance, or it may ignore it entirely, and by the time it returns with its data, the opportunity to explore that feature further may be gone. Communication itself is one of the most fundamental barriers. Water blocks the radio waves that carry signals through air and space, which means that most underwater communication relies on sound. Acoustic signals can travel long distances, but they are slow and low bandwidth. A simple text message sent to a satellite takes milliseconds. The same message sent to a deep-sea vehicle might take seconds or minutes. Transmitting high-resolution video is almost impossible. This means that many deep-sea missions are conducted blind, with vehicles carrying out their tasks largely on their own and reporting back only after surfacing. That delay makes real-time control difficult and limits our ability to adapt missions as they unfold. Durability is another major constraint. The deep ocean is not kind to machines. Pressure strains hulls and crushes components. Corrosive salt water eats away at metals and electronics. Sediment and biofouling can clog sensors and reduce efficiency. Even small leaks can become catastrophic under thousands of atmospheres of pressure. Designing vehicles that can survive these conditions for extended periods is a monumental engineering challenge. Most deep-sea missions last only a few days, and maintenance is frequent and costly. Long-term installations, instruments left on the seafloor for months or years, are rare and prone to failure. Even the cables that carry data from these instruments to shore can be damaged by shifting sediments, landslides, or curious animals. Then there's the question of precision. The deep ocean is a vast three-dimensional space, and exploring it requires not just reaching a location, but navigating and positioning accurately once there. On land, GPS provides precise location data. In space, star trackers and gyroscopes do the same. Underwater, GPS signals don't penetrate, and acoustic positioning systems are less precise and more complicated. A vehicle's position might drift by tens or hundreds of meters over the course of a mission, making it difficult to return to a specific site or correlate data with exact locations. Mapping fine-scale features, a hydrothermal vent, a coral mound, a methane seep, often requires painstaking manual work and repeated visits, each one consuming time, money, and energy. The scale of the ocean multiplies these problems. Covering even a small region in detail requires many missions, each one expensive and resource-intensive. Mapping a trench, for example, might take dozens of dives, each lasting days. Mapping an entire ocean basin would require thousands, and even then, the result would be incomplete. Water movement, sediment deposition, and geological activity can change the seafloor over time, erasing old features and creating new ones. Instruments left in place to monitor these changes must be robust enough to survive years in the deep, and many are not. Cost is perhaps the most mundane but also the most limiting factor. Deep-sea exploration is expensive on a scale few other scientific endeavours match. A single research expedition can cost millions of dollars, requiring specialised ships, trained crews, and months of planning. The vehicles themselves are expensive to build and maintain, and they often require costly recovery operations if they fail. Funding for such missions is limited, and competition for it is intense. This means that exploration is sporadic and uneven. Certain regions, those with obvious scientific or economic value, are studied in detail, while vast areas remain untouched simply because no one can afford to visit them. The limits of our machines don't just affect how much of the ocean we can explore, they shape how we interpret what we find. Because we can only observe small areas at a time, our understanding of the deep ocean is often based on snapshots rather than continuous coverage. We might study a hydrothermal vent field and assume it is typical, when in fact it could be unique. We might observe a current pattern in one place and assume it applies elsewhere, even though local conditions could be dramatically different. These biases are not the result of carelessness but of necessity. Our machines cannot yet provide the comprehensive, continuous data that would allow us to see the ocean as a whole. Instead, we piece together fragments and hope they add up to a coherent picture. Our reliance on machines also introduces a psychological limitation. Because we experience the deep ocean through the eyes of our devices, our sense of it is mediated and incomplete. We see what the cameras see, hear what the sensors record, measure what the instruments can detect. But the deep ocean is more than those measurements. It is a dynamic, living system, and much of its complexity may lie beyond the reach of our current tools. This isn't just a technical problem, it's a conceptual one. We may not even know what we're missing, because our machines cannot tell us what they are incapable of sensing. Some scientists hope that new technologies will bridge these gaps. Advances in battery technology could allow vehicles to stay at depth for weeks instead of days. Improvements in materials science could produce lighter, stronger hulls capable of withstanding greater pressures. Better acoustic systems might increase communication bandwidth. Artificial intelligence could make autonomous vehicles more adaptive and capable of making decisions in real time. And distributed networks of small, cheap sensors, sometimes called ocean swarms, could collect data over vast areas simultaneously. All of these ideas are promising, and some are already being tested. But they are incremental steps, not solutions. Even with better machines, the scale, complexity, and hostility of the deep ocean will remain daunting. Another fundamental problem is that most deep-sea technology is designed with specific missions in mind. A vehicle built to map the seafloor might not be equipped to study biology. One designed to sample water might not be able to collect rocks. Specialized instruments are more effective at their tasks, but they limit the scope of what a single mission can accomplish. Carrying multiple instruments adds weight and complexity, reducing efficiency. Swapping them requires bringing the vehicle back to the surface, which takes time and resources. As a result, exploration often happens in a piecemeal fashion, with different missions addressing different questions at different times. This fragmented approach makes it difficult to build a comprehensive understanding of the ocean as a system. Even the most advanced machines face the problem of unpredictability. The deep ocean is full of unknowns, unexpected currents, sudden changes in temperature or chemistry, shifting sediments, and life forms that behave in ways we don't anticipate. A vehicle programmed for a specific set of conditions may struggle when those conditions change. A current stronger than expected could push it off course. A sediment cloud could obscure its sensors. An encounter with a curious or aggressive animal could damage its equipment. Designing for every possibility is impossible, and so every mission carries an element of uncertainty. All of these factors combine to make the deep ocean one of the most difficult environments humans have ever attempted to explore. Space, for all its vastness, is simpler in many ways. It is mostly empty. Communication is fast, solar power is abundant, surfaces are static. The deep ocean, by contrast, is dense, dynamic, and hostile. It resists our machines at every turn. Every meter forward is a struggle, every discovery hard won. And even when we succeed, we do so in narrow windows with limited tools, gathering fragments of data from a world that dwarfs our capacity to measure it. This is why, despite decades of technological progress, most of the ocean remains unexplored. Our machines have carried us farther than we could ever go on our own, but they have not brought the ocean within our grasp. They are in a sense like lanterns carried into a vast cave, illuminating small patches while leaving most of the darkness untouched. And as the cave stretches on, twisting and branching into passages we can't even see, it becomes clear that no number of lanterns will ever light it all. Yet the limits of our machines are not the end of the story. They are part of a broader picture, one that includes not just technical and physical challenges, but also the fundamental nature of the ocean itself. Because even if we built perfect machines, vehicles that could dive forever, map with infinite precision, and never break, we would still face an ocean that is alive, moving, and constantly changing. Its currents shift, its chemistry evolves, its ecosystems grow and collapse, and that restless motion adds another layer of impossibility, one that technology alone can never solve. One of the most deceptive things about the ocean is how still it seems from the surface. Stand on a beach and watch the horizon, and the water looks eternal, unchanging, a vast blue expanse that has been there forever and will remain long after we're gone. The waves come and go in their timeless rhythm. The tides rise and fall as they always have. It's easy to believe that beneath that surface lies a world of permanence, but the truth is that the ocean is anything but still. It is a living, shifting system, constantly in motion at every scale, from the smallest eddies to the largest planetary currents. It changes by the minute, by the season, by the century. And that perpetual change is one of the biggest reasons why exploring the whole ocean will always remain beyond our reach. To understand why, we have to think about the ocean not as a static body of water, but as a dynamic engine, driven by forces that operate on timescales ranging from seconds to millennia. The water itself is always moving, shaped by winds, tides, the rotation of the earth, differences in temperature and salinity, and the gravitational pull of the moon and sun. These forces create a complex web of currents that crisscross the globe, connecting distant regions and carrying heat, nutrients and life across thousands of kilometers. The Gulf Stream, for example, transports warm water from the tropics to the North Atlantic, moderating the climate of Europe. The Antarctic Circumpolar Current circles the southern continent, linking the Atlantic, Pacific and Indian Oceans into a single interconnected system. Together, these currents form the ocean's circulatory system, a vast dynamic network that influences weather, climate and life itself. But the ocean's motion is not just horizontal, it is vertical too, and that vertical movement is just as important and just as complicated. Warm, less dense water tends to rise, while cold, dense water sinks. This creates overturning currents that move water between the surface and the deep. One of the most important of these is the thermohaline circulation, a global conveyor belt that carries water around the world in a loop that can take centuries to complete. Water sinks in the North Atlantic, travels deep beneath the ocean to the southern hemisphere, and eventually rises again in the Pacific and Indian Oceans. This circulation regulates global temperatures, stores carbon, and redistributes nutrients. It is also sensitive to changes in temperature and salinity, meaning that as the climate changes, so too does the conveyor belt's strength and pattern. Even at smaller scales, the ocean is in constant flux. Internal waves ripple through the deep, invisible from the surface, but capable of carrying enormous amounts of energy. Eddies, swirling masses of water tens or hundreds of kilometers across, break off from major currents and wander the ocean for weeks or months before dissipating. Tides flow into and out of bays, estuaries and continental shelves, altering local conditions twice a day. Upwelling events bring cold, nutrient-rich water to the surface, fueling blooms of plankton that support entire ecosystems. Downwelling pushes oxygen-rich surface water into the deep, sustaining life far below. These processes overlap and interact in ways that are complex and often unpredictable, creating a constantly shifting mosaic of physical, chemical and biological conditions. For scientists trying to study the ocean, this motion is both a blessing and a curse. It is a blessing because it drives the systems that make the ocean so vital to life on Earth. It is a curse because it makes the ocean almost impossible to pin down. Measurements taken at one time and place may be obsolete a day later or a few kilometers away. A current that was strong and stable last year might weaken or change course this year. A region that was rich in nutrients one season might be barren the next. Even the deep ocean, which once seemed stable and unchanging, is subject to slow but significant shifts over time. Water masses mix and move, sediment accumulates and erodes. Chemical gradients shift as circulation patterns evolve. The ocean is not a fixed entity waiting to be mapped and catalogued. It is a moving target, and that motion ensures that any map, any measurement, any exploration is only a snapshot of a moment that will soon pass. This constant change complicates every aspect of exploration. Mapping the seafloor, for example, is difficult enough in static conditions, but when currents move sediment around, reshape features, and bury or expose geological structures, the task becomes even harder. A ridge mapped one year might look different the next. A canyon shape might shift after a submarine landslide. Even the location and intensity of hydrothermal vents can change, as tectonic activity opens new pathways for fluids and seals old ones. These changes don't just alter the landscape, they alter the ecosystems that depend on it. A vent field that supported a thriving community of organisms might go dormant, forcing them to migrate or die out. A new vent might create a new habitat, drawing colonizers from miles away. Life in the deep ocean is intimately tied to the physical environment, and as that environment changes, so too does the distribution of life. Currents also complicate the task of deploying and operating instruments. Moorings, anchored instruments that measure temperature, salinity, currents and other properties, can be pushed off course or buried by sediment. Drifting sensors can be carried far from their intended paths. Autonomous vehicles may find themselves in unexpected locations after being swept by powerful flows. Even communication cables can be damaged or displaced by shifting sediments and strong currents. These challenges mean that maintaining long-term monitoring networks is difficult and expensive. Instruments must be regularly checked, repaired, and recalibrated, and even then, data gaps are common. The ocean's chemistry is also constantly evolving. Changes in temperature, pressure, and biological activity affect how gases dissolve and how nutrients cycle. Carbon dioxide levels in the atmosphere influence how much of the gas is absorbed by the ocean, altering its acidity. As the ocean becomes more acidic, it affects the ability of organisms like corals and shellfish to build their skeletons and shells. Oxygen levels too are changing. Warming reduces the solubility of oxygen in seawater and alters circulation patterns that deliver oxygen to the deep. Expanding oxygen minimum zones, regions where oxygen levels are too low to support most marine life, are altering ecosystems and shifting the distribution of species. These changes happen on timescales ranging from years to centuries, but they mean that the ocean we explore today is not the same as the one we will explore tomorrow. The biological side of the equation is equally dynamic. Ocean ecosystems are in constant flux, responding to physical and chemical changes as well as to their own internal dynamics. Plankton blooms can appear and disappear in a matter of days, driven by changes in nutrients, light, and temperature. Fish populations migrate with shifting currents and water masses. Predators follow prey. Entire ecosystems can collapse if key species decline or disappear. Human activities add another layer of change. Overfishing, pollution, and climate change all alter the structure and function of marine communities, sometimes in unpredictable ways. Coral reefs bleach and die as waters warm. Invasive species spread to new regions, disrupting local food webs. Plastic debris accumulates in ocean gyres, creating new habitats for microorganisms and altering surface ecosystems. All of these changes ripple through the ocean, creating feedback loops that further complicate the picture. Climate change is perhaps the most profound driver of change in the modern ocean. Rising temperatures are altering circulation patterns, shifting habitats, and changing the timing of seasonal events like plankton blooms. Melting ice is adding fresh water to the ocean, affecting salinity and density, which in turn influence currents. The retreat of sea ice in the Arctic is opening new pathways for water to flow between the Atlantic and Pacific, potentially altering global circulation. Sea level rise is reshaping coastlines and changing the dynamics of estuaries and continental shelves. These changes are not uniform. Some regions are warming faster than others, and some are becoming fresher while others become saltier. The result is an increasingly complex and unpredictable ocean, one that is evolving in ways we are only beginning to understand. This unpredictability is a major obstacle to exploration. To truly understand the ocean, we need long-term data, measurements that capture its variability over seasons, years, and decades. But collecting such data is difficult and expensive, especially in remote and deep regions. Instruments must be deployed and maintained over long periods, often in harsh conditions. Ships must revisit the same locations again and again, which requires funding and logistical support. Satellites can provide some information, but they are limited to the surface and near-surface layers. As a result, our knowledge of how the deep ocean changes over time is fragmentary at best. We have snapshots of specific places at specific times, but we lack the continuous records that would reveal the full story. The dynamic nature of the ocean also means that our models, the mathematical tools we use to simulate and predict its behaviour, are always imperfect. Models rely on data to describe the current state of the ocean and to validate their predictions. But when data are sparse or outdated, the model's accuracy suffers. Small errors can grow over time, leading to large uncertainties in predictions. This is particularly problematic for long-term forecasts, such as how the thermohaline circulation will respond to climate change, or how oxygen levels in the deep ocean will evolve. Without comprehensive, high-quality data, these predictions remain uncertain, and because the ocean is constantly changing, even the best models must be updated regularly to remain relevant. The ever-changing nature of the ocean also challenges how we think about exploration itself. On land, exploration often means discovering something and then moving on, secure in the knowledge that what we've found will still be there when we return. A mountain doesn't move, a canyon doesn't disappear. But in the ocean, what we find today may not exist tomorrow, or it may exist in a different form. A current we mapped might shift course, a vent we studied might go silent, a species we observed might migrate or vanish. Exploration here is not about uncovering static truths, but about tracking dynamic processes. It is less like cataloguing a library and more like trying to follow the plot of a story that is still being written. This fundamental difference means that complete exploration, in the sense of fully mapping, understanding and describing the ocean, may be impossible even in principle. The ocean is not a puzzle with a fixed solution. It is a system in flux, always evolving, always changing. Even if we could map every metre of the seafloor, catalogue every species, and measure every current today, that knowledge would begin to age the moment it was collected. New features would form, old ones would disappear, species would evolve, currents would shift, our understanding would always lag behind reality, chasing a moving target that can never be fully caught. This doesn't mean exploration is futile. On the contrary, the ocean's dynamism is part of what makes it so fascinating and so vital. Studying how it changes helps us understand the planet as a whole. It reveals how climate systems work, how life adapts, how geological processes shape the Earth. It gives us clues about the past, recorded in sediments and water masses, and warnings about the future. And even if we can never know the ocean completely, each new piece of knowledge adds to our ability to live with it, use it wisely and protect it from harm. But it does mean that exploration must be seen not as a finite task, but as an ongoing process. There will never be a moment when we can say, we have explored the ocean. There will always be new questions, new changes, new mysteries to investigate, and that endlessness is part of the reason why exploring the whole ocean is impossible. The ocean is not just vast and deep. It is alive, in constant motion, changing beneath our feet and before our eyes. It defies completion by its very nature. And yet, even this restless, shifting character is only part of the story. Because beyond the physical and biological changes lies another barrier, one rooted not in the ocean itself but in us. Our exploration is shaped by our priorities, our resources, our politics, and our choices. The ocean is too vast and too complex for any one nation, any one organisation or any one generation to explore alone, and so our efforts are fragmented, uneven, and often short-lived. The limits of our will and our coordination are as real as the limits of our technology, and they too play a part in making the dream of fully exploring the ocean forever out of reach. If the vastness of the ocean's waters and the complexity of its motion make exploration difficult, and if pressure and terrain set physical limits on what we can reach, there remains another frontier that might be the most elusive of all: life itself. For most of human history, we assumed that we had a fairly complete understanding of where life exists and what forms it takes. We imagined that life clustered where sunlight penetrates, that the deep ocean was barren, and that the range of biological diversity was something we could eventually count and categorize. That view has turned out to be wildly incomplete. The more we look, the more we discover that the ocean is teeming with life in places we never expected, in forms we never imagined, and in numbers far beyond what we can catalogue. Most of that life remains invisible to us, not because it is rare, but because we have not yet found ways to see it. And it is this hidden frontier, perhaps more than any other, that underscores why exploring the whole ocean may be impossible. Our ideas about marine life have been shaped by the environments we can easily access. The sunlit surface layers, rich with photosynthesis, are home to an astonishing variety of organisms, everything from microscopic phytoplankton to massive whales. Coral reefs, coastal shallows, and open water ecosystems support complex food webs that we have studied for centuries. But beyond the reach of light, life takes on entirely different forms, adapted to conditions that would kill most surface organisms in seconds. It is there, in the darkness and the pressure, that the ocean becomes truly alien. One of the most surprising revelations of modern oceanography is just how much life exists far from sunlight. The discovery of hydrothermal vent ecosystems in the late 1970s shattered the long-held assumption that sunlight was the foundation of all life on Earth. At depths of more than 2 kilometers, where no light penetrates and pressures exceed hundreds of atmospheres, scientists found thriving communities built not on photosynthesis, but on chemosynthesis, the ability to derive energy from chemical reactions rather than sunlight. Bacteria living near the vents use hydrogen sulfide and other chemicals spewed from the Earth's crust to fuel their metabolism, forming the base of a food web that includes giant tube worms, clams, crabs, and fish. These ecosystems are so isolated and so unlike anything found elsewhere that many of the species discovered there exist nowhere else on Earth. The implications of that discovery were profound. It suggested that life could exist wherever chemical energy is available, even in places previously thought uninhabitable. It hinted that similar ecosystems might exist on other worlds, on Europa, Enceladus, or other icy moons with subsurface oceans. And it revealed how much we still don't know about the deep ocean. Hydrothermal vents are not rare, but they are scattered unpredictably along mid-ocean ridges and volcanic regions. Many remain undiscovered, hidden miles below the surface. Each new vent field that is found hosts unique communities, often with species unknown to science. And because the deep ocean is so vast, we have likely seen only a tiny fraction of what's out there. Hydrothermal vents are not the only example of life thriving in unexpected places. Cold seeps, regions where hydrocarbons like methane and hydrogen sulfide leak from the seafloor, support their own unique ecosystems, also based on chemosynthesis. Whale falls, the carcasses of whales that sink to the seafloor, become islands of life, sustaining specialized communities for decades as they decompose. Even small patches of rock or debris on the abyssal plains can serve as oases for sessile organisms. Everywhere we look in the deep ocean, life has found a way to adapt, exploit, and persist. The scale of this unseen biodiversity is staggering. Scientists estimate that as much as 90% of species in the ocean remain undescribed. Many of these are small, microscopic plankton, bacteria, and archaea that drift invisibly through the water or live in sediments. But others are larger and more complex, simply inhabiting regions we rarely explore. Every deep-sea expedition seems to uncover new species, from bizarre gelatinous creatures to fish with never-before-seen adaptations. And those discoveries are not slowing down. If anything, they are accelerating as new tools allow us to sample more efficiently and in more remote regions. The pattern is clear. The more we look, the more we find, and the more we realize how much we have missed. Even the life we think we know turns out to be more complex than we imagined. The ocean's microbial communities, for example, are astonishingly diverse and play critical roles in global processes. They drive nutrient cycling, mediate chemical reactions, and form the base of many food webs. Yet they are so small and so varied that we have only begun to scratch the surface of their diversity and function. Metagenomic studies, which analyze the collective genetic material of microbial communities, routinely reveal thousands of new species and genes. Many of these genes have unknown functions, suggesting biochemical pathways and adaptations that we have never seen before. These discoveries hint at an oceanic biosphere far richer and more intricate than anything we've mapped. The sheer abundance of microbial life is almost beyond comprehension. A single litre of seawater can contain more than 1 billion microorganisms. The global ocean contains an estimated 10 to 129 microbial cells, a number so vast that it exceeds the number of stars in the observable universe. These microbes are not evenly distributed. They form complex, shifting communities that vary with depth, temperature, nutrient availability, and countless other factors. Sampling them is difficult, and understanding their dynamics is even harder. Each sample represents a snapshot in space and time, and conditions can change dramatically over short distances and periods. This means that our knowledge of microbial life in the ocean is not just incomplete, it is a fraction of what's out there. The unknown extends beyond microbes. Deep-sea fishes and invertebrates exhibit adaptations so strange they seem to defy biology as we know it. Some have transparent bodies, others produce light in intricate patterns, some have jaws that can unhinge to swallow prey larger than themselves, others drift motionless for days, conserving energy in an environment where food is scarce. Entire lineages may exist that we have never encountered, isolated in remote regions or in habitats too extreme for our current technology to reach. The possibility of undiscovered megafauna, large animals unknown to science, is not as far-fetched as it might seem. The coelacanth, a prehistoric fish thought to have gone extinct 66 million years ago, was rediscovered alive in 1938. Giant squid, once dismissed as sailors' myth, were photographed alive for the first time only in the 21st century. If such large and conspicuous creatures could remain hidden until recently, how many smaller and subtler species still escape detection? Even the basic patterns of biodiversity in the deep ocean remain mysterious. On land, biodiversity tends to peak in tropical regions and decline toward the poles. In the ocean, the patterns are more complex and less predictable. Some deep-sea regions are hotspots of diversity, while others are sparsely populated. The factors driving these patterns — temperature, nutrient availability, pressure, geological activity — interact in ways we don't fully understand. Because our sampling is so limited, we may be missing entire biogeographic regions and evolutionary lineages. Each new expedition has the potential to rewrite our understanding of how life is distributed in the deep sea. Exploring this invisible frontier is extraordinarily challenging. Sampling biological communities at great depth requires specialized equipment capable of withstanding extreme pressure and preserving specimens in their natural state. Many deep-sea organisms are fragile and disintegrate when brought to the surface. Others die when pressure is reduced, leaving only fragments for study. Capturing microbes and viruses, which are orders of magnitude smaller, presents even greater difficulties. Contamination is a constant concern, and distinguishing native organisms from those introduced by sampling equipment can be difficult. Even when we succeed in collecting samples, analysing them requires advanced molecular tools and computational methods. Sequencing the DNA of a microbial community can reveal thousands of species, but interpreting that data, understanding what those species do, how they interact, and how they fit into the broader ecosystem is a massive and ongoing effort. Our limited access to the deep ocean also means that we have sampled only a tiny fraction of its habitats. Most of our knowledge comes from areas near mid-ocean ridges, continental slopes, or other regions of interest. Vast stretches of abyssal plain and deep basin remain virtually unstudied. Even within well-studied regions, sampling is sparse. A handful of cores or trawls might represent thousands of square kilometres. It's as if we were trying to understand the biodiversity of a rainforest by examining a few square metres of soil. The picture we build from such limited data is inevitably incomplete and possibly misleading. This uncertainty extends to the ocean's evolutionary history. The deep sea has existed for hundreds of millions of years, serving as both a refuge and a crucible for life. Many lineages may have originated there, evolving in isolation and leaving few traces in the fossil record. Others may have retreated into the deep as surface conditions changed, surviving in hidden refuges while disappearing from shallower waters. Because sediment accumulates slowly in the deep ocean and is rarely disturbed, the seafloor holds an unparalleled archive of Earth's biological and climatic past. But drilling into that archive is difficult, expensive, and rare. As a result, our understanding of deep-sea evolution is fragmentary. Entire chapters of life's story may lie buried beneath kilometers of water and sediment, waiting for tools and missions that may never come. The unknown life of the ocean is not just a scientific curiosity, it has practical implications for humanity. Many marine organisms produce unique chemicals with potential applications in medicine, from antibiotics to anti-cancer drugs. Others have enzymes that function under extreme conditions, useful in industrial processes. Microbial communities play critical roles in global nutrient cycles and climate regulation. The more we learn about these organisms, the more we realize how deeply our lives are intertwined with theirs, yet the vast majority remain undiscovered, their potential untapped. The invisible frontier is not just a scientific challenge, it is a missed opportunity. The possibility of undiscovered life also shapes how we think about exploration itself. If most of the ocean species remain unknown, then our picture of how marine ecosystems function is necessarily incomplete. Food webs, nutrient cycles, evolutionary relationships, all of these are built on assumptions that may change as new species are discovered. This means that our current models of how the ocean works may be missing key pieces. Some processes we attribute to physical or chemical forces may, in fact, be driven by biology. Some apparent anomalies in nutrient distribution or carbon cycling may be the result of unseen microbial activity. Without a fuller picture of life in the ocean, our understanding of the ocean as a system will always be partial. Even our sense of where life can exist is still evolving. The discovery of organisms living deep within oceanic crust, in rock pores kilometers below the seafloor, has expanded the known limits of the biosphere. These microbial communities exist in darkness, under immense pressure, with minimal energy. Yet they survive, perhaps even thrive, in conditions that would once have seemed impossible. Their existence suggests that the ocean's biosphere extends far deeper and farther than we ever imagined. It also raises profound questions about the origins of life and its potential distribution in the universe. If life can exist here, what other hidden habitats might it occupy, both on Earth and beyond? This frontier of unseen life highlights a paradox at the heart of ocean exploration. The more we learn, the more we realize how much we don't know. Every new discovery expands the horizon of the unknown rather than shrinking it. Each time we find a new species, we must ask how many more are out there. Each time we identify a new ecosystem, we must wonder how many others remain hidden. The unknown is not a shrinking frontier at the edge of knowledge. It is an expanding one that recedes as we approach it. And that is perhaps the most humbling lesson the ocean teaches us. Exploration is not a process of conquering the unknown, but of revealing its depth. The more we uncover, the deeper it becomes. The invisible frontier of life is not a blank space waiting to be filled. It is a vast, dynamic, ever-changing realm that may never be fully mapped or understood. And even if we could somehow catalogue every species alive today, evolution would continue to create new ones, and environmental changes would drive others to extinction. The ocean's biodiversity is not a static inventory. It is a living, evolving process, as boundless and dynamic as the water itself. This makes the task of exploring the ocean fundamentally different from exploring most other environments. It is not just about reaching new places or measuring new features. It is about grappling with the limits of what we can perceive and comprehend. It is about accepting that the unknown is not a temporary obstacle but a permanent feature of the landscape. And it is about understanding that the most profound mysteries may not lie in distant galaxies or exotic planets, but right here, beneath our feet, in the waters that cover most of our world. And yet, even this unseen life, as vast and mysterious as it is, represents only part of the challenge, because exploring the whole ocean is not just a question of what exists out there. It is also a question of what we, as a species, choose to do. Our tools, our priorities, our politics, and our ambitions shape what we explore and what we leave unknown. And those human limits, just as much as the physical ones, ensure that the ocean will always hold secrets beyond our reach. For all the staggering forces at work in the deep, the crushing pressure, the endless darkness, the shifting currents, the labyrinthine terrain, and the unseen biodiversity, one of the most decisive limits on ocean exploration does not come from the ocean at all. It comes from us. The human factor is both the reason we know anything about the ocean and the reason we will likely never know it completely. Our curiosity drives us to explore, but our priorities, politics, economies, fears, and limitations shape how far we go and how much we are willing to invest. The ocean is vast beyond measure, but the scope of our exploration is ultimately determined by human decisions, and those decisions, more than any single physical barrier, may be what keeps the ocean forever partly unknown. Curiosity has always been one of humanity's most powerful forces. It's what carried us out of caves and across continents, what sent ships across uncharted seas and rockets into space. It's what drives scientists to peer through microscopes and telescopes alike. The desire to understand the world, to know what lies beyond the horizon, is woven into who we are. That same impulse fuels ocean exploration. Every dive into the deep is an act of curiosity, a refusal to accept ignorance, a declaration that we want to know. It's what pushed Jacques Piccard and Don Walsh into the Challenger Deep in 1960, what sent James Cameron back more than half a century later, what propels research vessels into remote waters and keeps scientists awake for days at a time analysing the data they bring back. Without that drive, none of what we know about the ocean would exist. But curiosity is only one part of the equation. Exploration also requires resources: ships, submersibles, laboratories, sensors, satellites, and people. And those resources are finite. They must compete with other demands: defense budgets, healthcare systems, education, infrastructure, space exploration, and more. Even within the realm of science, oceanography must share funding with fields like medicine, physics, and astronomy. The result is that ocean exploration, despite its importance, is often underfunded and underprioritized. Many research vessels operate on limited schedules because there isn't enough money to keep them at sea year-round. Expeditions are delayed or cancelled due to lack of funding. Instruments remain on wish lists because budgets don't allow them to be built. The cost of deep-sea exploration is staggering. A single research cruise can cost millions of dollars. Building and operating a deep-diving submersible can cost tens or even hundreds of millions. Maintaining a fleet of autonomous vehicles, satellites, and support infrastructure requires long-term investment. These costs are justified by the knowledge gained, but they limit how much exploration can be done. Scientists must prioritize, choosing which regions to study and which questions to pursue. Many areas are never visited simply because there isn't enough funding to go everywhere. The result is a patchwork of exploration, detailed knowledge in some places, near total ignorance in others. Politics further complicates the picture. The ocean covers more than 70% of Earth's surface, but it is divided by invisible lines of national jurisdiction. Coastal nations control the waters up to 200 nautical miles from their shores. They're exclusive economic zones, EEZs, and can regulate access to those regions. Beyond that lies the high seas, an international commons governed by treaties and conventions. In theory, this shared ownership should encourage collaboration. In practice, it often leads to conflict, competition, and caution. Nations are reluctant to share data that might have strategic or economic value. Disputes over territorial claims can limit exploration in contested areas. Political instability can make certain regions inaccessible. Even international research efforts can become entangled in bureaucracy and diplomatic wrangling. This fragmentation of authority means that ocean exploration is unevenly distributed. Wealthier nations with advanced technology conduct most deep-sea research, while poorer nations often lack the resources to explore even their own waters. International collaborations exist, but they can be difficult to coordinate and sustain. Data sharing is inconsistent and standards vary. As a result, vast areas of the ocean, particularly in the southern hemisphere and around developing nations, remain largely unexplored. The gaps in our knowledge are not evenly spread. They mirror the gaps in our political and economic systems. National priorities also shape the direction of exploration. Governments tend to fund projects that promise practical benefits: navigation, fisheries management, mineral exploration, climate modelling, over those that are purely driven by curiosity. Fundamental research into the deep ocean, while scientifically valuable, often struggles to compete with projects that have immediate economic or strategic payoffs. This skews our exploration efforts towards certain goals and away from others. It means that some areas are studied because they might yield resources, while others are ignored because they do not. It means that we may know more about a seamount with potential mineral deposits than about a nearby trench that holds unique ecosystems. Commercial interests play a growing role as well. Companies are increasingly looking to the deep ocean for resources, not just fish, but minerals, oil, and gas. Deep-sea mining, once a distant concept, is now on the horizon, with firms exploring ways to extract metals like cobalt, nickel, and rare earth elements from the sea floor. These resources are crucial for technologies like batteries, electronics, and renewable energy systems. But the pursuit of profit can come at the expense of science. Exploration driven by commercial goals may prioritize resource extraction over environmental understanding. It may focus on regions with economic potential while ignoring others. It may even keep data proprietary, limiting its availability to the broader scientific community. Human risk is another major factor. Deep-sea exploration is inherently dangerous. The conditions are extreme, the equipment is complex, and the margin for error is small. A minor malfunction can mean the loss of a vehicle, and in crewed missions, the loss of lives. The implosion of the Titan submersible during a 2023 dive to the Titanic wreck served as a stark reminder of those risks. Such incidents shape public perception and influence funding decisions. They also impose ethical constraints. How much risk is acceptable in the pursuit of knowledge? How much should we spend to minimize that risk? These questions have no easy answers, but they weigh heavily on the future of exploration. Public interest plays its part too. Ocean exploration struggles to capture the popular imagination in the same way space exploration does. The images returned from Mars rovers or distant galaxies are dramatic and easily understood, while the complexities of deep-sea ecosystems or oceanic circulation patterns are harder to communicate. This affects funding and political support. Projects that capture the public's attention are more likely to receive money and backing. Those that do not may struggle, no matter how scientifically valuable they are. The irony is that the ocean is far more important to our daily lives than distant planets. It regulates our climate, provides food, and sustains biodiversity. Yet it often remains out of sight and out of mind. Education and awareness shape this dynamic. Many people grow up knowing more about the surface of Mars than about the bottom of the Pacific. School curricula devote limited time to oceanography. Media coverage of ocean science is sporadic. The result is a public that often underestimates the importance of the ocean and the scale of the mysteries it holds. Without broad understanding and support, exploration efforts struggle to gain momentum. Scientists can advocate, but they cannot explore without the backing of societies that value and invest in that work. Even when the will exists, coordination is difficult. Ocean exploration is inherently global. Currents do not respect national borders, ecosystems span thousands of kilometers, and changes in one region can ripple across the planet. Effective exploration requires collaboration on a scale that is difficult to achieve. Data must be shared. Standards must be harmonized. Missions must be coordinated, yet political rivalries, economic competition, and bureaucratic inertia often stand in the way. International initiatives like the United Nations Decade of Ocean Science for Sustainable Development aim to bridge these gaps, but progress is slow and uneven. The ocean demands cooperation, but humanity often struggles to provide it. Our limitations are not just external, they are also internal. Exploration requires imagination, persistence, and patience. It requires thinking in terms of decades and centuries, not election cycles or fiscal years. It requires valuing knowledge for its own sake, even when the practical benefits are not immediately clear. These are not qualities that come easily to our species. We are often short-sighted, focused on immediate concerns rather than long-term goals. We are often reactive, responding to crises rather than anticipating them. We are often divided, pursuing narrow interests rather than shared ones. These tendencies make sustained, coordinated exploration difficult. The ocean scale exacerbates these human limitations. It is hard to build political momentum around something so vast and distant. It is hard to maintain funding for missions that might take years to plan and execute, and yield uncertain results. It is hard to sustain public interest in a frontier that is invisible and inhospitable. And because the ocean is not static, because it is always changing, exploration is not something that can be done once and completed. It must be continuous, and continuity is one of the hardest things for humans to achieve. Cultural perceptions also shape how we approach the ocean. For centuries, the deep sea was seen as a hostile alien realm, a place of monsters and mysteries best left alone. Even today, the language we use reflects that sense of otherness. We speak of the deep as inhospitable, unforgiving, alien. These perceptions influence priorities. They make the ocean seem distant from human concerns, a realm apart rather than an integral part of our planet's systems. Changing that mindset is essential if exploration is to advance, but changing cultural attitudes is slow work. Our relationship with the ocean is further complicated by the ways we exploit it. Fishing, shipping, oil drilling, and mining all compete with exploration for space, resources, and attention. In some cases, these activities directly interfere with scientific work. Noise from shipping, for example, can disrupt acoustic surveys. Pollution can alter ecosystems before they are studied. Overfishing can remove key species, changing the dynamics of food webs. In other cases, exploitation and exploration are in tension at a broader level, as governments and companies prioritize economic gain over scientific understanding. Balancing these interests is a constant challenge. Ethics also play a role. The deep ocean is home to ecosystems and species that have existed undisturbed for millions of years. Our presence, even as explorers, has the potential to disrupt them. Vehicles can stir up sediment, damaging delicate filter feeders. Sampling can remove rare organisms. Noise and light can alter behaviour. As we push deeper and farther, we must grapple with questions about how much disturbance is acceptable in the pursuit of knowledge. These ethical considerations can limit where we go, how we study, and what we are willing to do, and rightly so. But they also mean that some parts of the ocean may remain off limits, either by choice or by consensus. The human factor also includes the limits of our imagination. We tend to design missions based on what we already know, to look for what we expect to find. But the deep ocean is full of surprises, and many of its secrets may not be where or what we anticipate. Truly transformative discoveries often come from looking in unexpected places or asking unconventional questions. But doing so requires a willingness to take risks, to invest in projects that might fail, to challenge assumptions. These are not easy choices for institutions constrained by budgets, oversight, and accountability. And yet, for all these limitations, the human factor is not just a barrier. It is also the reason exploration happens at all. It is humans who dream of what lies beneath. It is humans who design and build the machines that dive into the dark. It is humans who spend months at sea, who pore over data for years, who piece together the fragments of knowledge into a picture of the deep. Our weaknesses constrain us, but our strengths push us forward. Curiosity, ingenuity, and perseverance have already revealed wonders that previous generations could scarcely imagine. They will reveal more, but those revelations will never be complete. The same forces that drive us to explore will also inevitably limit how far we can go. That is the paradox at the heart of ocean exploration. The ocean is too vast, too deep, too complex, too dynamic, and too alive for any one species, even one as inventive as ours, to fully comprehend. And we ourselves are too divided, too short-sighted, too limited to overcome those challenges completely. The ocean's mysteries are not just a reflection of its nature, they are a reflection of ours. They are the mirror it holds up to humanity, showing us both the reach of our ambition and the boundaries of our capacity. But even with those boundaries, we keep going. We send ships to map unknown seamounts. We drop sensors into abyssal trenches. We launch fleets of drifting floats to measure temperature and salinity across the globe. We train new generations of scientists to ask questions their predecessors never imagined. Each mission, each measurement, each discovery is a step forward, small on its own, but part of a larger journey. And that journey does not end. Because even if the whole ocean cannot be explored, it can always be explored more deeply, more broadly, more thoughtfully than before. And perhaps that is the real lesson of the human factor. The limits we face are real, but they are not reasons to stop. They are reminders of the scale of the challenge and the humility it demands. They are the conditions under which exploration happens, and they point us toward the final piece of this story, the recognition that some mysteries are not meant to be solved, that impossibility itself is not a failure but a feature of the world we inhabit. The ocean's secrets are endless, not because we lack the will or the tools, but because the ocean is a living, changing, infinite system, and that endlessness is precisely what keeps us returning to it, again and again. There's a certain point in every conversation about the ocean where the discussion stops being about data, tools, and logistics and starts becoming something deeper. It's the moment when the sheer size of the unknown overwhelms our usual categories of thought, when we realize that this isn't just a technical problem waiting to be solved, but something far more fundamental. The ocean is not only a frontier of science or an obstacle to exploration, it is a mirror of mystery itself. It represents the limits of our knowledge, the persistence of the unknown, and the humbling fact that some parts of reality might always remain beyond our grasp. The more we study it, the more we are forced to confront a truth that is both unsettling and beautiful. The ocean is not simply another thing to explore, it is the final mystery of our planet. To understand why, it helps to look at how our relationship with the ocean has evolved over time. For most of human history, the sea was a boundary, the edge of the known world. It separated continents, cultures, and ideas. It was both a highway and a barrier, a source of food and a source of fear. Ancient myths are full of sea monsters, storms, and unknowable depths. Even as navigation improved and explorers began to cross the oceans, the deep remained mysterious. Ships sailed over vast stretches of water with no idea what lay beneath them. Entire continents could be mapped before anyone had even glimpsed the world a few kilometers below the waves. It was only in the last century or so that we began to truly peer into that hidden realm. And even now, after decades of technological progress and scientific discovery, we have explored only a tiny fraction of it. That fact alone is staggering. More than 80% of the ocean floor remains unmapped in high resolution. The majority of deep-sea ecosystems have never been observed. Entire geological features have been detected only indirectly, their details unknown. Most species that inhabit the ocean remain undiscovered. We know more about the surface of Mars than we do about the bottom of our own planet's seas. These numbers are often repeated, and they should be. because they capture the scale of what we're dealing with, but the deeper implication is not just that the ocean is unexplored, it's that it may be inherently unexploitable in full. The task may not simply be unfinished, it may be unfinishable. The reasons are not mysterious in themselves. They are the ones we've already traced. The crushing pressures that make deep exploration difficult, the darkness that swallows light and sight, the shifting terrain that defies mapping, the limitations of our machines, the ceaseless motion of the water, the unimaginable diversity of life, the constraints of our politics and priorities. Each of these on its own is formidable. Together, they create a barrier that is more than just practical. It is conceptual. It suggests that the very idea of complete exploration may not apply here. The ocean is not a puzzle to be solved once and for all. It is a dynamic system, a living planet within a planet, whose complexity grows as we learn more about it. This is why, even as our technology improves and our maps become more detailed, the unknown does not shrink as much as we expect. It shifts, it deepens, it expands into new dimensions. A detailed sonar map reveals a trench we didn't know existed, and that trench contains ecosystems we haven't studied. A genetic survey uncovers thousands of new microbial species, and those species hint at biochemical processes we don't understand. A current is measured more precisely, and that precision reveals new interactions with the atmosphere and the climate. Every answer opens up new questions, and those questions often turn out to be larger than the ones we started with. This is not unique to ocean science. The same thing happens in astronomy, particle physics, and biology. But the ocean is perhaps the most vivid example, because it is so close and so vast at the same time. It's right here, covering most of our planet, shaping our weather, influencing our climate, sustaining our lives. It is not distant like a galaxy or invisible like a quark. It laps at our shores and fills our skies with rain, and yet it remains, in so many ways, a stranger. The fact that something so essential, so omnipresent, and so intimately tied to our existence could remain so profoundly mysterious is both humbling and awe-inspiring. It also forces us to rethink what exploration means. When we speak of exploring something, we often imagine a process that ends. We think of explorers planting flags on mountaintops, of cartographers filling in blank spaces on maps, of scientists cataloguing species into neat taxonomies. Exploration, in that sense, is a process of completion, a transition from unknown to known, from mystery to mastery. But the ocean resists that narrative. It does not become simpler as we study it. It does not yield its secrets in a linear progression. It remains dynamic, elusive, and in many ways, unknowable. Exploration here is not about conquering mystery, but about learning to live within it. This reframing has profound implications. It suggests that the goal of ocean exploration is not to finish the job, because that job cannot be finished, but to deepen our relationship with the unknown. It suggests that the purpose is not to erase mystery, but to engage with it more fully, to understand its contours, its patterns, its implications. It suggests that exploration is not a march toward a final destination, but a conversation that evolves over time, and it suggests that the unknown is not a failure of knowledge, but an essential part of what knowledge is. This perspective also sheds light on why the ocean has such a powerful hold on the human imagination. It is not just a physical space. It is a metaphor for the unknown itself, vast, deep, and always beyond reach. Writers, poets, and philosophers have long turned to the sea to express the human relationship to mystery, and with good reason. The ocean's surface may be familiar, but its depths remain alien. Its rhythms are predictable, but its moods are not. It sustains life, but it can also destroy it. It is both known and unknowable, comforting and terrifying, constant and ever-changing. In this way, it mirrors the larger mysteries of existence, time, consciousness, the origins of life, that we grapple with but never fully solve. The ocean's role as a final mystery is not just philosophical, it has practical consequences. Because the unknown is so vast, we must accept that our knowledge will always be partial. Our models of ocean circulation will always have uncertainties. Our maps will always have gaps. Our understanding of biodiversity will always be incomplete. This does not mean that science is futile. On the contrary, it means that science is an ongoing process rather than a finished product. It means that we must constantly refine, revise, and expand our knowledge. It means that humility must be a core part of our approach. The humility to recognize that we will never know everything, and the curiosity to keep seeking nonetheless. This humility is especially important because the ocean is not just a mystery for its own sake. It is deeply intertwined with human life and planetary systems. It regulates the climate by absorbing heat and carbon dioxide. It produces half the oxygen we breathe. It supports billions of people through fisheries and coastal economies. It shapes weather patterns, influences rainfall, and stores vast amounts of energy. Our future, our survival, is tied to the ocean's health and stability. Yet our ignorance of it remains profound. We cannot predict its long-term changes with confidence. We cannot fully assess the impacts of our actions on its ecosystems. We cannot even say how many species live within it. This gap between dependence and understanding is one of the defining challenges of our time. It also raises questions about responsibility. If the ocean is the final mystery, then our approach to it must reflect that. We cannot treat it as a resource to be exploited without understanding. We cannot assume that our interventions will have predictable outcomes. We cannot assume that we are in control. Instead, we must approach the ocean as a partner, vast, powerful, and full of unknowns. We must recognize that our actions ripple through systems we do not fully comprehend, and we must balance our desire to explore with a commitment to protect, to preserve the very mystery that draws us. This balance is not easy. It requires us to rethink how we value knowledge and how we make decisions. It requires us to support exploration even when the benefits are not immediately clear, to fund research that may not yield quick results, to cooperate across borders and disciplines. It requires us to accept that exploration is not a race with a finish line, but a shared endeavour with no end. And it requires us to see mystery not as an obstacle, but as an invitation, a chance to expand our understanding, to challenge our assumptions, to grow as a species. There is also something deeply human about our relationship with the ocean as mystery. Mystery is what drives us to ask questions, to build tools, to venture into the unknown. It is what pushes us beyond the boundaries of what we know and forces us to imagine what lies beyond. Without mystery, there is no curiosity. Without curiosity, there is no discovery. And without discovery, there is no growth. The ocean's refusal to yield all its secrets is not a frustration, but a gift. It ensures that there will always be new questions to ask, new wonders to uncover, new reasons to look beyond the horizon. And perhaps this is the most important reason why exploring the whole ocean is impossible. It is not just that the task is too big, the conditions too harsh, the technology too limited. It is that the ocean itself is not a fixed thing to be fully known. It is a living, changing, evolving system that defies finality. Even if we could map every seafloor feature, discover every species, and measure every current, the ocean would continue to change. New features would form, new species would evolve, new patterns would emerge. The mystery would remain, not because we failed, but because that is the nature of the ocean, and, in a way, the nature of reality itself. This perspective transforms the way we think about impossibility. When we say that exploring the whole ocean is impossible, we often hear that as a limitation, as something that stops us from achieving a goal. But impossibility can also be a kind of freedom. It means that exploration is not a task to be completed, but a journey to be continued. It means that there will always be more to learn, more to discover, more to wonder at. It means that the story of the ocean, and our story within it, has no final chapter. And in that sense, The ocean is not just the final mystery of Earth. It is a reminder of the role mystery plays in all of science, all knowledge, all human endeavour. It reminds us that the unknown is not a void to be filled, but a presence to be engaged with. It reminds us that mastery is not the same as understanding, and that understanding itself is never complete. It reminds us that humility and curiosity are not opposites, but partners. And it reminds us that our search for knowledge is not about eliminating mystery, but about deepening our relationship with it. Seen this way, the impossibility of fully exploring the ocean is not a failure. It is a reflection of the ocean's nature and of ours. It is a sign that we live in a world that is richer, deeper, and more complex than we can ever fully grasp. It is a sign that there will always be something new to learn, something new to explore, something new to imagine. And it is a sign that the story of exploration, of the ocean and of ourselves, is far from over. And as we continue that story, we come to a final realization. The impossibility of fully exploring the ocean does not diminish its value. If anything, it enhances it. The unknown is not an absence, but a presence, not a void, but a vastness. It gives the ocean its depth, its beauty, its power to inspire. It is what keeps us returning to the shore, staring out at the horizon, and wondering what lies beyond. And in that sense, the ocean's greatest gift to us is not its resources or its influence or even its role in sustaining life. Its greatest gift is its mystery, the reminder that no matter how much we learn, there will always be more to discover. And as that mystery endures, it leads us inevitably toward the final part of this journey. Because the impossibility of exploring the whole ocean is not just about the ocean itself, it is also about us, about our need to accept limits, to live with uncertainty, to find meaning not just in answers, but in questions. It is about learning to see mystery not as a failure of knowledge, but as the heart of knowledge itself. And it is about recognizing that even if we never reach the end of the ocean story, the act of seeking it is worth everything. There's something inevitable about the human urge to finish things. We build monuments to completion. We celebrate the end of journeys, the solving of puzzles, the discovery of answers. We plant flags, write final chapters, and mark the moment when something unknown becomes known. It's built into our stories and our science alike, the idea that if we try hard enough, long enough, we can reach the end of any road. And yet, when it comes to the ocean, that instinct runs into something immovable. Because the ocean is not a road, it's not a problem with a solution, or a map with an edge. It's not even a single thing. It's a shifting, living, evolving system that will always be larger, deeper, and more complicated than we are. And that means that the shore we imagine, the point at which the whole ocean is explored and known, is one we will never reach. This is not a failure of technology or effort. It's not that we haven't tried, or that we won't continue to try. Humanity has been exploring the sea for as long as it has existed as a species. Our ancestors paddled out into coastal waters long before written history. Ancient civilizations mapped coastlines and sailed beyond the horizon. The great age of exploration saw ships cross entire oceans, linking continents and cultures. The 20th century brought submarines that could dive thousands of meters and satellites that could scan the surface from space. In the 21st century, autonomous vehicles and genetic sequencing have opened new windows into the deep. Each of these steps has pushed the boundary of the known further out. And yet, the horizon remains as distant as ever. That horizon is not a line we can cross. It's a feature of the landscape itself. Always ahead, always receding as we move forward. Every new tool we invent, every new expedition we launch, every new discovery we make brings the unknown into sharper focus, but does not reduce it. The more we learn, the more we realize how much there is left to learn. This is the paradox of exploration. Knowledge does not shrink mystery, it multiplies it. And nowhere is that more true than in the ocean. Consider what happens every time we probe deeper. We map a stretch of seafloor and find unexpected ridges, trenches or vents. We send a submersible into a trench and find species that no one has ever seen before. We analyse a water sample and find genetic sequences from organisms we cannot identify. We deploy a sensor network and detect currents that don't match our models. Each of these discoveries is valuable, but each one also points beyond itself to new questions and new unknowns. The ocean is not just unknown because it is unexplored. It is unknown because it is inexhaustible. It contains layers of complexity that branch and deepen endlessly, no matter how far we go. Even our most ambitious visions of exploration acknowledge this. International initiatives to map the seafloor by 2030, for example, aim to provide a baseline, not a final product. They recognise that the ocean will continue to change, that maps will need constant revision, that discovery will continue beyond any deadline. Long-term ecological monitoring programs accept that they will never capture every fluctuation in biodiversity or chemistry. They aim instead to reveal patterns, not to exhaust them. Even the boldest proposals for deep-sea colonization or mining are premised on the idea that we will interact with only a small fraction of what exists. The dream of total knowledge, of a final, finished picture, is absent from serious plans, because those who work most closely with the ocean understand how impossible that dream is. And yet, even as we accept that we will never reach the end, we keep going. There's something deeply human in that persistence. We build telescopes even though we know the universe is infinite. We study consciousness even though we may never fully understand it. We explore the ocean even though we know we will never finish exploring it. The act itself matters. The journey matters. The pursuit of knowledge is not only about reaching an endpoint, it's about deepening our relationship with the world around us. It's about learning enough to live wisely within our limits, enough to protect what we depend on, enough to be humbled by what we cannot control. In that sense, the impossibility of fully exploring the ocean is not a defeat. It's a condition of the work itself. It's what makes the work meaningful. If there were an end, if there were a final shore to reach, the story would stop there. But there isn't. The ocean will continue to change, and we will continue to change, and the relationship between the two will continue to evolve. Each generation will inherit a different ocean and ask different questions of it. Each will discover things the previous generation could not imagine. Each will add to the story, knowing that the story will never be complete. That ongoing story is not just about curiosity, it's about survival. The ocean is not a distant frontier. It's the foundation of life on Earth. It regulates the climate, supports the food chain, cycles nutrients, and produces oxygen. Our future depends on its health and stability. But we cannot protect what we do not understand. The more we learn about the ocean, about its currents, its chemistry, its biodiversity, its geology, the better equipped we are to make decisions that safeguard it. Exploration is not just an intellectual pursuit, it's a practical necessity. It's how we anticipate changes, adapt to them, and mitigate the harm we cause. And yet, our understanding will always be incomplete. We will always be reacting to changes we don't fully predict, managing systems we don't fully comprehend. That uncertainty is not comfortable. It challenges our desire for control, our preference for clear answers, our habit of thinking in terms of solutions. But it is the reality we live with, and learning to navigate it is one of the most important skills we can develop. The ocean teaches us that we must act even without full knowledge, that we must care for what we cannot fully know, that we must accept uncertainty without surrendering to it. It also teaches us something about perspective. Our species tends to think of itself as the centre of things, the pinnacle of evolution, the masters of technology, the shapers of the planet's future. The ocean reminds us that we are small. It existed long before us and will exist long after us. It has shaped continents, climates, and species for billions of years. It is the cradle of life and the engine of planetary systems. We are part of it, dependent on it, but we are not in charge of it. Its scale dwarfs us. Its power humbles us. Its mystery puts our ambitions in perspective. This humility is not a weakness, it is a strength. It grounds our actions in reality and reminds us of the scale of the world beyond ourselves. In a way, the impossibility of fully exploring the ocean is a reminder of the nature of existence itself. We live in a universe that is larger, older, and more complex than we can comprehend. There will always be questions we cannot answer, phenomena we cannot predict, realms we cannot reach. The ocean is our local version of that cosmic truth, a vast, dynamic, unknowable system that surrounds us and sustains us, always inviting us to learn more, always reminding us that we will never learn it all. That is not a reason to despair. It's a reason to keep asking questions, to keep building, to keep exploring. It's a reason to embrace mystery as a fundamental part of the human experience. There's also a paradox here worth noticing. The fact that we will never explore the whole ocean is, in a sense, what makes exploration worthwhile. If we could finish it, if we could someday declare that there were no more mysteries left, the journey would lose its purpose. It would become a historical footnote rather than a living pursuit. The endlessness of the ocean's mysteries ensures that exploration remains vibrant and alive. It guarantees that there will always be something new to discover, some new frontier to push against, some new question to ask. It keeps the human spirit of inquiry alive, generation after generation. And this brings us back to the idea of the shore we'll never reach. It's not a physical shoreline, not a place on a map. It's the metaphorical horizon of complete knowledge, the fantasy of total mastery. It's the idea that we could ever know the ocean so thoroughly that there would be nothing left to learn. That shore does not exist. Not because we are failing to reach it, but because it recedes forever as we move forward. Every step toward it creates more distance. Every answer multiplies the questions. The pursuit is endless because the ocean itself is endless in its complexity. And yet this endlessness is not frustrating if we approach it in the right way. It's liberating. It means that there will always be something new to strive for. It means that our curiosity will never run out of material. It means that the act of exploration can be valuable in itself, even if it never ends. It means that mystery is not the enemy of knowledge, but its companion. The shore we will never reach is not a failure to arrive. It's the reason to keep going. This understanding reshapes how we think about progress. Too often we measure progress in terms of endpoints. Goals achieved, tasks completed, problems solved. But the ocean shows us a different model. Progress here is not about completion, but about deepening. It's about building better tools, asking better questions, seeing more clearly, understanding more deeply. It's about refining our models and expanding our maps, even if they will never be perfect. It's about embracing uncertainty and complexity, not eliminating them. And it's about recognizing that each generation's work builds on the last, creating a legacy of knowledge that will never be finished but will always be growing. And in this light, the impossibility of fully exploring the ocean is not discouraging. It's inspiring. It means that the work of exploration is endless, and that there will always be room for new explorers, new questions, new discoveries. It means that no matter how much we learn, the unknown will always be larger, and that's not a problem to solve but a reality to celebrate. It means that the ocean will always be a source of wonder, challenge, and humility, and it means that our relationship with it will always be dynamic, always evolving, always alive. Perhaps that is the true gift of the ocean. It teaches us to live with mystery. It teaches us to value the journey even when there is no destination. It teaches us to seek understanding not as a way to conquer the unknown, but as a way to live alongside it. It teaches us that limits are not the end of possibility, but the framework within which possibility thrives. And it teaches us that our curiosity, our endless desire to know, to understand, to reach beyond ourselves, is not diminished by impossibility. If anything, it is strengthened by it. So maybe the shore we'll never reach is not something to mourn, but something to cherish. It is the horizon that keeps us moving, the goal that gives meaning to the journey, the mystery that makes exploration worth doing. It is the reminder that the ocean is not ours to master, but ours to learn from, to live with, to protect. It is the proof that the world is bigger than we are, that there is always more beyond what we know, and it is the invitation to keep going, to keep asking, to keep seeking. Not because we will ever arrive, but because the act of seeking is what makes us who we are. And in that sense, the impossibility of exploring the whole ocean is not the end of the story. It is the story. It's the thread that connects our past to our future, from the first humans who gazed out at the waves with wonder, to the generations yet to come who will send new machines into the deep. It's what ties our small individual lives to the vast unfolding history of the planet. It's what keeps the horizon alive. And it's why, even though the shore will always remain just beyond reach, we will never stop walking toward it.